In Lua, print hello world is a statement that prints the string hello world to the standard output. The print function is a built-in function in Lua, which means you don't need to define it yourself. It's available by default. Print, this is the name of the function. Hello world. These parentheses contain the argument passed to the print function. In this case, the argument is the string hello world. When you run this Lua script, it will output hello world to the console or terminal. The print function is commonly used for debugging, testing, or simply displaying information during the execution of a Lua script. In Lua, you can use either single quotes or double quotes to delimit strings. Both of these are valid ways to write a print hello world. Both of these examples will produce the same output, hello world. To include a double quote within a string, the character must be escaped. Escaping a character means the character will be treated as part of the string rather than a Lua instruction. To escape a character, follow the steps. The backslash is used to escape the inner double quotes, indicating that they are part of the string and not the string delimiters. Using the escape character is a good practice when you need to include quotes within a string, and it helps avoid confusion or potential syntax errors. In this line, the single quote within the string "It's a lovely day" is not escaped because the string itself is enclosed in double quotes. This line prints the string "It's a lovely day," including the apostrophe without issue. In Lua, both single and double quotes can be used to delimit string literals. The choice between them often depends on the need to include one type of quote within the string without escaping it and personal preference. The escape character backslash is used to include special characters within strings without causing syntax errors or prematurely terminating the string. In programming, variables act as containers, holding and managing data within a program. They provide a way to store, manipulate, and access values, allowing developers to work with dynamic information. Variables in Lua, like containers, can be filled with different types of data, such as numbers, strings, or booleans, offering flexibility in handling diverse information within a program's execution. Data types define the nature of information in a programming language. In Lua, there are fundamental data types such as numbers, representing integers or floating point values, strings, encapsulating sequences of characters, and booleans, representing true or false values. These data types serve as the building blocks for manipulating and processing information within a program, allowing developers to work with a variety of data and perform operations tailored to each type. Understanding data types is essential for effective programming and enables precise handling of diverse data scenarios. Declaring a variable in Lua involves specifying its name and, optionally, its scope using the local keyword. For example, local age declares a variable named age with local scope. Assigning a value to a variable is done using the assignment operator =, like age equals 25. This associates the value 25 with the variable age. Combining declaration and assignment allows developers to create and initialize variables, providing a foundation for storing and manipulating data in Lua programs. Local and global scope in Lua refer to the visibility and accessibility of variables within different parts of a program. Local scope, variables declared with a local keyword are local to the block or function in which they are defined. They are accessible only within that specific block or function. Local scope helps prevent unintended variable clashes and promotes encapsulation. Global scope, variables declared without the local keyword have global scope. They are accessible throughout the entire program, from any block or function. Global variables can be convenient but may lead to naming conflicts and make code harder to maintain. Choosing between local and global scope depends on the desired visibility and the need for encapsulation. Local scope is often preferred to avoid unintended side effects and improve code maintainability. Coercion to string in Lua involves converting a variable of another data type into a string. This can be achieved by using the concatenation operator dot. For example, if age is a number, age equals age. Years coerces it to a string by appending the string years. Lua's dynamic typing allows such conversions, enabling flexibility when working with different data types within a program. However, it's important to use coercion judiciously to ensure compatibility and clarity in the code. In Lua, nil signifies the absence or undefined state of a value. It is often used to initialize variables without assigning a specific value. Understanding nil is crucial for handling situations where a variable lacks a defined data reference, ensuring clarity in program logic. The type function in Lua is used to determine the data type of a given variable. It returns a string representing the type of the variable. In this example, type value will return the string number, indicating that the variable value is of type number. The function is useful for dynamic type checking in Lua programs. Type conversion, also known as typecasting, involves changing the data type of a variable. In Lua, type conversion often occurs implicitly when performing certain operations, such as concatenating a string with a number. However, explicit type conversion can be done using functions like tonumber and tostring. In the first part, Lua implicitly converts the string 42 to a number when adding it to 8. In the second part, tostring explicitly converts the number 25 to a string. Understanding when and how type conversion occurs is important for working with diverse data types in Lua. Both toString and toNumber are built-in functions in Lua. They come as part of the standard Lua library and are available for use without requiring any additional modules or external dependencies. These functions are fundamental for explicit type conversion and are commonly used in Lua programming. In this tutorial, we explored essential tools for managing data types in Lua. The type functions served as our guide, revealing the nature of variables. We then harness the power of toString for explicit type conversion, enabling precision in data manipulation. Let's solve our first problem. Our task: simple sum. Create a Lua script to accomplish the following. Define two numbers as strings. Convert these strings to numbers. Sum the numbers. Print the result. Pause the video and spend 5 minutes to solve this, then come back to see my solution. As we move on to step 1, let's define our two numbers as strings. Now, in step 2, notice how we're using tonumber to convert these strings, stored in variables number1 and number2, into actual numeric values. This is a crucial step for numerical operations in Lua. Keep an eye on how this conversion sets the stage for our sum calculation in the next step. Let's dive right into it. As we reach the final step, observe how effortlessly we sum up number 1 and number 2 using a straightforward addition operation. The converted numeric values seamlessly flow into our result variable. Simplicity in action. In the last step, witness the magic as we print the result of our sum. Using the print function, we display the outcome, showcasing the power of converting and manipulating variables in Lua. Great job! In programming, comments serve as textual annotations within the code, providing context, explanations, or notes. They are essential for enhancing code readability, documenting logic, and facilitating collaboration among developers. In Lua, comments come in two main forms: single-line comments and multi-line comments. Single-line comments allow you to add brief explanations or notes on a single line of code. Single-line comments are useful for providing context, documenting variables or functions, and enhancing the readability of your Lua script. Multiline comments can span multiple lines, providing a convenient way to add more extensive explanations, document entire sections of code, or temporarily disable blocks of code during debugging. Multiline comments contribute to clear and detailed documentation, making your Lua script more comprehensible. Comments during debugging play a crucial role in Lua programming. By strategically placing comments, you can temporarily exclude or include sections of code, making it easier to identify and troubleshoot issues. Commenting out specific lines or blocks allows you to isolate potential problems, test alternative solutions, and communicate debugging notes to yourself and other developers. Welcome to our Lua journey. Today, we're diving into the dynamic world of mathematical operators. These powerful symbols empower you to perform various arithmetic feats in your Lua scripts. From addition to exponentiation, each operator plays a unique role in shaping the behavior of your code. Get ready to explore the language of numbers in Lua and unlock new possibilities in your programming endeavors. Let's embark on this mathematical adventure together. Addition, denoted by the plus symbol in Lua, combines numeric values, seamlessly bringing them together to create a sum greater than its parts. Subtraction, symbolized by minus, is the art of taking away one value from another in Lua. It's a fundamental arithmetic operator that provides a concise way to find the difference between two numbers. Multiplication, represented by asterisk, is the catalyst for growth. This essential arithmetic operator allows us to efficiently scale numeric values, unlocking the potential for repeated addition. Division, marked by slash, introduces the concept of sharing and partitioning. This fundamental arithmetic operator divides one value by another, guiding us through the realm of proportions and ratios. Floor division, the hidden gem denoted by double slash, takes Lua arithmetic to a new level. Unlike regular division, it rounds down to the nearest whole number, offering precision in discrete calculations. Modulo, signal by %sign, introduces a fascinating twist to Lua arithmetic. This operator calculates the remainder after division, a useful tool for cyclic patterns and repetitive tasks. Exponentiation, the power-packed operator often known as the caret or hat symbol, is Lua's gateway to magnifying numbers. It raises a base value to the power of an exponent, unleashing the potential for exponential growth. Negation, characterized by the hyphen symbol, is a way of flipping the sign on numeric values. It transforms positivity into negativity and vice versa, offering a quick change of direction in your Lua code. In Lua, math operators are the silent architects shaping numeric landscapes. From the simplicity of addition to the intricacies of exponentiation, each symbol carries the power to transform numbers. Embrace these operators as your tools of precision, opening doors to limitless mathematical possibilities in your Lua scripts. Understanding variable usage in Lua. When you use the same variable multiple times, its value is determined by the most recent assignment. Let's illustrate this concept with examples. In example 1, the value of number is updated by adding 3 to its current value. In example 2, the double dot operator concatenates world to the existing value of message. Example 3 demonstrates how x is modified based on its initial value and the result of the multiplication with y. Understanding this behavior is crucial for effective variable manipulation in Lua. In Lua, when you declare the same variable multiple times, the most recent assignment takes precedence. Let's look at the next example. In this example, Lua reads the code from top to bottom. Despite having multiple declarations of variable, the final assignment is local variable equals 4, and it overrides the previous values. Therefore, when you print the value of variable, it reflects the most recent assignment, which is 4. In Lua, both the concatenation operator double dot and the comma operator can be used for combining values, but they serve different purposes. The double dot operator is specifically designed for string concatenation. It concatenates two strings together. The comma is typically used for separating arguments in function calls or items in a list. When used in a print statement, it automatically adds a space between values. In the first part, concatenates strings to form a full name. In the second part, the comma automatically adds spaces between variables when using print. In Lua, as in standard mathematical conventions, multiplication and division take precedence over addition and subtraction. This means that expressions involving multiplication and division are evaluated before addition and subtraction. However, you have the flexibility to alter the default priority of operations by using parentheses. When you enclose expressions in parentheses, Lua evaluates them first, overriding the default order of operations. This provides control and clarity in complex mathematical expressions. Relational operators in Lua are symbols that allow you to compare values and make logical decisions based on their relationships. Here's a brief overview. Equality checks if two values are equal. Inequality checks if two values are not equal. Greater than checks if the left operand is greater than the right. Less than checks if the left operand is less than the right. Greater than or equal to checks if the left operand is greater than or equal to the right. Less than or equal to checks if the left operand is less than or equal to the right. In this example, relational operators are used to compare number 1 and number 2. The results are stored in Boolean variables and then printed to the console. This demonstrates how relational operators help in making logical comparisons between values in Lua. Relational operators play a crucial role in decision-making, allowing you to create conditions based on the comparison of values in Lua scripts. Practice session task. Step 1. Create two variables and assign a numerical value to each one. Step 2. Do an arithmetic operation with the values and store the result in a new variable. Step 3. Convert the result to a string. Step 4. Create a Boolean variable that. Apply a relational operator between the two variables. Step 5. Use a single print statement to display the type of the converted result itself, and the Boolean value. Pause the video and spend 5 minutes to try to solve the task, then come back to see my solution. Here is my solution. Note, in this solution, the variable names x, y, z, bool and specific numeric values are arbitrary. Feel free to use your own variable names and numbers when applying these concepts to your projects. Choose meaningful names for your variables to enhance code readability. Customize the code to fit your project requirements. Experiment with different numeric values to observe how the code behaves. Understand the impact of using different relational operators for Boolean conditions. Ensure the print statement accurately reflects the type and value of the converted result and the Boolean. Don't hesitate to modify the code, make mistakes, and learn from the process. These concise notes guide viewers on what aspects to focus on and be mindful of during their practice session. In Lua, input-output operations are crucial for interacting with the console. io.write allows you to output text to the console, while io.read enables you to receive input from the user. Let's explore how these functions work and how you can leverage them to create more interactive Lua programs. While both print and io.write are used for outputting text to the console, there's a key difference between them. Print automatically adds a new line character after each output, making it convenient for displaying separate lines of text. On the other hand, io.write does not automatically add a new line, allowing you more control over the formatting of your output. This subtle difference makes io.write ideal for scenarios where you want to display text without starting a new line. In the first example using print, each call to print outputs text on a new line, automatically adding a new line character at the end of each string. In the second example using io.write, both hello and world are output on the same line because io.write does not automatically add a new line character. It's up to the programmer to manually control the formatting of the output. At the following example, io.write outputs the prompt enter your name to the console. Local name io.read reads input from the user, allowing them to enter their name. The entered text is stored in the variable name. Next, io.write outputs a greeting message, including the entered name. The double dot operator concatenates strings, and \n adds a new line character to start a new line. io.read is used to capture input from the user. It reads input from the console, allowing users to enter text or data, which can then be stored in variables or processed further in the Lua script. Remember, the \n represents a new line character in Lua. When used within a string, it signifies the start of a new line in the output. Input-output operations are essential for creating interactive programs in Lua. They enable communication between the program and the user, allowing for dynamic interaction. This interaction enhances the user experience, making programs more versatile and user-friendly. Practice session task. 1. Use output to ask the user for their full name. 2. Use input to store the user's name. 3. Use output to ask the user for their birth year. 4. Use input to store the user's birth year. 5. Store the present year in a new variable. 6. Calculate the user's age based on the present year and the provided birth year. 7. Output the user's name and age. Pause the video and take your time to solve the task, then come back to see my solution. Here is my solution. First, we use io.write to prompt the user to enter their full name. Next, we use io.read to capture the user's input and store it in a variable called name. Then, we use io.write again to prompt the user to enter their birth year. We use io.read once more to capture the user's input for their birth year and store it in a variable called birth_year. To calculate the user's age, first we store the present year, 2024, in a variable called present_year. Using the present year and the user's birth year, we calculate the user's age by subtracting the birth year from the present year. We convert the input to a number using tonumber to ensure proper arithmetic. Finally, we choose between to use print or io.write to display the user's name and calculated age on the screen. Congratulations on completing this tutorial. You've learned how to interact with users through input and output operations in Lua. Remember to practice what you've learned and experiment with different scenarios to deepen your understanding. Stay curious and keep exploring Lua's capabilities. Happy coding! Welcome to another session in our Lua Basics tutorial series. In this session, we'll be diving into the world of conditional statements in Lua. Conditional statements allow us to make decisions in our code based on certain conditions, enabling our programs to respond dynamically to different situations. Today, we'll be focusing on three essential conditional statements: if, Elseif, and else. These statements form the backbone of conditional logic in Lua and are used extensively in programming tasks of all kinds. In this example, we first define a variable called number and assign it a value of 10. Next, we use an if statement to check if the number is greater than 0. If this condition is true, we print the number is positive. If the number is not greater than 0, we use an Elseif statement to check if it is less than 0. If this condition is true, we print the number is negative. If neither of the previous conditions is true, we execute the else block and print the number is 0. This example demonstrates how. If, Elseif, and else statements allow us to evaluate multiple conditions and execute different blocks of code based on those conditions. In Lua, we can use multiple Elseif statements to evaluate additional conditions if the initial if condition is not met. This allows us to handle multiple possible outcomes in our code. For example, suppose we want to classify a given number into different categories based on its value range. We can use multiple Elseif statements to check each range sequentially and execute different actions accordingly. In this example, we use multiple Elseif statements to check if the number falls into different ranges number. Each Elseif statement is evaluated sequentially, and the corresponding block of code is executed if the condition is true. Using multiple Elseif statements allows us to create more complex conditional logic and handle various scenarios in our Lua scripts. In Lua, the end keyword is used to mark the end of a conditional block of code, such as an if, Elseif, or else statement. It serves as a delimiter to indicate where the block of code associated with the conditional statement ends. For example, in the following code snippet, the end keyword closes the entire conditional block, encompassing all the if, Elseif, and else statements. It helps Lua distinguish the boundaries of the conditional logic and ensures that the interpreter knows when to stop processing the conditions. Remember to always include an end keyword to close every conditional block in Lua to avoid syntax errors and ensure proper code execution. These fundamental concepts are essential building blocks for creating dynamic and responsive Lua scripts. As you continue your journey in Lua programming, remember to practice writing conditional logic in different scenarios to solidify your understanding. Practice session task 1. Prompt the user to enter the first number. 2. Read and store the user's input for the first number. 3. Prompt the user to enter the second number. 4. Read and store the user's input for the second number. 5. Compare the two numbers and determine which one is greater. Note: use if statements. Pause the video and take your time to solve the task. Here is my solution. Before we begin, it's important to note that the examples used in this tutorial are arbitrary and can be replaced. Feel free to experiment with different values, prompts, and variables to test the script and better understand its functionality. Let's start by prompting the user to enter the first number. We'll use io.write to display a message asking for input. Now, we'll read the user's input for the first number using io.read and store it in a variable. Next, we'll prompt the user to enter the second number in a similar manner as before. We'll read the user's input for the second number and store it in another variable. Now that we have both numbers, let's compare them to determine which one is greater. We'll use if statements for this. Now, let's test all possible scenarios to ensure our script works correctly. We'll test cases where the first number is greater, the second number is greater, and when both numbers are equal. In conclusion, we've successfully created a Lua script that prompts the user to enter two numbers and determines which one is greater. In this tutorial, we'll be diving into logical operators in Lua. Logical operators allow us to combine and manipulate Boolean values, enabling us to make more complex decisions in our code. By understanding how logical operators work, you'll be able to write more efficient and expressive Lua scripts. Let's explore these powerful tools together. First, we will define two Boolean variables, named isRaining and isCold, and we will store true for isRaining and false for isCold. Now, let's move on to the next step. We'll use if statements to check if our statements about the weather are true. The AND logical operator in Lua is used to combine two Boolean expressions. It returns true only if both expressions are true, otherwise it returns false. So, when we use the AND operator, both conditions must be met for the overall expression to be considered true. Once again we will use if statements, but this time we will use OR operator. The OR logical operator in Lua is used to combine two Boolean expressions. It returns true if at least one of the expressions is true, and false only if both expressions are false. So, when we use the OR operator, if either condition is met, the overall expression is considered true. Once again we will repeat the process, but this time we will use NOT operator. The NOT logical operator in Lua is used to negate a Boolean expression. It returns true if the expression is false, and false if the expression is true. So, when we use the NOT operator, it reverses the truth value of the expression. In conclusion, logical operators are powerful tools in Lua that allow us to combine and manipulate Boolean values to make more complex decisions in our code. By understanding how AND, OR, and NOT operators work, you can write more expressive and efficient Lua scripts. Experiment with different combinations and scenarios to deepen your understanding of logical operators. Thank you for joining me in this tutorial, and I look forward to seeing you in the next one. In today's tutorial, we're diving into the world of string manipulation in Lua. Strings are fundamental data types in Lua, and understanding how to work with them effectively is essential for any Lua programmer. We'll explore a range of powerful string functions provided by Lua's standard library, allowing you to manipulate and transform strings with ease. So let's jump right in and uncover the secrets of Lua's string functions. All over this tutorial, we'll be working with a variable called sample string that contains hello world. This string will serve as our playground for exploring the various string manipulation functions provided by Lua. We'll apply these functions to sample string to demonstrate their capabilities and see how they can be used to transform and analyze strings in Lua. So let's get started by delving into the fascinating world of string manipulation. Let's take a closer look at string.lower. This handy function allows us to transform any string to lowercase, making comparisons and data processing more flexible and consistent. Now, let's shift our focus to string.upper. This versatile function enables us to convert any string to uppercase, providing a standardized format for our data. By using string.upper, we can ensure uniformity in our text processing tasks and streamline our code. Next on our list is string.match. This function offers powerful pattern matching capabilities, allowing us to extract specific substrings or patterns from a given string. With string.match, we can search for and retrieve targeted information from our data, enhancing our ability to parse and analyze text. To use string.rep, to repeat a string multiple times, you simply provide two arguments. The first argument is the string you want to repeat. The second argument is the number of times you want to repeat the string. String.reverse. This function allows us to reverse the characters in a string, transforming ABC into CBA. By leveraging string.reverse, we can quickly manipulate the order of characters within a string to suit our needs. By utilizing string.sub and its arguments, we can precisely control which portion of the string to extract. The function takes two arguments, the start index and the end index. These indices determine the range of characters to be included in the extracted substring. With this flexibility, we can tailor our substring extraction to meet specific requirements and extract the precise data we need. Moving on to string.gsub, we encounter a powerful tool for string manipulation. This function allows us to globally substitute occurrences of a pattern within a string with a specified replacement. With string.gsub, we can efficiently perform find and replace operations on strings, making bulk modifications and transformations a breeze. Let's now explore string.gmatch, a versatile function for pattern matching in strings. This function iterates over all occurrences of a specified pattern within a string, allowing us to extract multiple substrings or capture groups. With string.gmatch, we can efficiently parse and process complex text data, enabling advanced pattern-based operations. The string.byte is one of the most widely used Lua string library functions that takes a character or a string as an argument and then converts that character into its internal numeric representations. Moving on to string.char, we encounter a function that performs the inverse operation of string.byte. while string.byte retrieves the ASCII value of a character, string.char converts an ASCII value into its corresponding character. This function facilitates the creation of strings from ASCII values, allowing for flexible string manipulation and construction. Let's now discuss string.find, a function designed to locate patterns within strings. With string.find, we can search for a specified pattern within a string and retrieve the indices of its occurrence. This function provides valuable functionality for text processing tasks, enabling us to identify substrings, extract data, and perform pattern-based operations efficiently. Next up, we have string.len, a straightforward function that returns the length of a string. With string.len, we can easily determine the number of characters in a given string, providing valuable insight into the size and structure of our textual data. This function serves as a fundamental tool in string processing, enabling us to perform length-based operations and validations with ease. String.format is used to create a formatted string. The format string in this example today is %s, the %dth day of the year. %s is a placeholder for a string value. %d is a placeholder for an integer value. The values Monday and 7 are provided as arguments to string.format. Monday replaces the %s placeholder, and 7 replaces the %d placeholder. The resulting formatted string is stored in the variable formatted string. Finally, the formatted string is printed to the console using print. Before we wrap up, I want to emphasize that while these string manipulation functions may seem complex at first glance, they're actually quite intuitive and powerful tools for working with text data. In fact, we'll be diving deeper into each of these functions in future tutorials, with plenty of examples to help solidify your understanding. So stay tuned for more practice and exploration. See you in the next tutorial. Before we continue, I encourage you to pause the video and take a moment to explore different approaches to the problem we're solving. Remember, programming is all about problem solving, and there's often more than one way to achieve a goal. Feel free to experiment with different variable names, string manipulations, and logic structures. Don't hesitate to seek out solutions online or in documentation if you get stuck. This is your opportunity to practice your skills and discover what works best for you. Once you've had a chance to explore, come back and compare your solution with what we'll cover next. Let's dive in. The expression tonumber, name, not equal nil checks if the variable name can be converted into a number using the tonumber function. Here's how it works. Tonumber, name this attempts to convert the value of name into a number. If name contains a valid numerical value, tonumber returns that value as a number. If name cannot be converted to a number, tonumber returns nil. Tonumber, name, not equal nil. This compares the result of tonumber, name, to nil. If tonumber, name, successfully converts name into a number, the result will not be nil, indicating that name contains a numerical value. If name cannot be converted to a number, the result will be nil. So, tonumber, name, not equal nil is a way to check if name contains a numerical value. If it does, the script converts it into a string using tostring, name, to ensure consistency in further processing. If name does not contain a numerical value, it remains unchanged as a string. In our example, string.upper is used to convert the user's input for their name to uppercase. This ensures consistency in handling the name regardless of whether the user enters it in lowercase, uppercase, or a mix of both. By converting the input to uppercase, we simplify the process of checking and comparing the user's response later in the dialog. Next, we will check if the user has entered a name. If the name is empty, it prompts the user to enter a name. Otherwise, it greets the user with their name and asks if they would like to continue. It then reads the user's response and converts it to lowercase for consistency. Let's break down the logic step by step. First, we will check if the user's name is empty. This is done using the condition if name it is equal to an empty string. If the user's input for the name is an empty string, the script proceeds to prompt the user to enter a name. Otherwise, it moves on to greet the user with the entered name and continue with the dialog. Step 2, we will handle the case when the name is empty. If the user's name is empty, it prints a message informing them that they didn't enter a name. This is accomplished with io.write, you didn't enter a name. In step 3, we will greet the user and ask for further interaction. If the user's name is not empty, the script greets the user with their name. Then it prompts the user with a question, would you like to continue? Yes/no. Step 4, we will read the user's response. It reads the user's response using io.read and stores it in the variable response. Step 5, we will convert the response to lowercase. To ensure consistency, the script converts the user's response to lowercase using string.lower response. This allows the script to handle both uppercase and lowercase input from the user in a uniform manner. Overall, this logic ensures that the script interacts with the user effectively, handles empty inputs appropriately, and maintains consistency in processing user responses. In the last part of our script, we will check first if the user wants to continue. This is done using the if, Elseif, and else statements. It checks the value of the variable response, which stores the user's input. If the user's response is yes, the script proceeds to execute the corresponding block of code. If the response is no, it executes another block of code. If the response is neither yes nor no, it executes a default block of code to handle invalid responses. Next, we will handle the case when the user wants to continue. If the user responds with yes, the script prints a message indicating that the user wants to continue. The message is displayed using io.write, great. Let's continue. This encourages the user to proceed with whatever action or dialogue is being presented. After that, we will handle the case when the user does not want to continue. If the user responds with no, the script prints a farewell message. The message is displayed using io.write, understood. Goodbye. This informs the user that the interaction or process has concluded. Now we will handle invalid responses. If the user's response is neither yes nor no, the script prints a message indicating that the response is invalid. The message is displayed using io.write, not a valid response. This prompts the user to provide a valid response, ensuring that the script can proceed accordingly based on the user's input. Overall, this part of the script efficiently handles the user's response and provides appropriate feedback based on their input, ensuring a smooth and interactive user experience. Note: the reason there are two end statements at the end of the script is to close both the else block and the if statement inside it. The first end corresponds to closing the else block, which encompasses the code that executes if the user's name is not empty. The second end corresponds to closing the if statement that checks if the user wants to continue. This if statement is nested inside the else block. Having two end statements ensures that both the else block and the nested if statement are properly closed, maintaining the correct structure and flow of the code. Using string.lower and string.upper in Lua scripts can enhance the user experience and improve script functionality by standardizing input and ensuring consistency. These functions are particularly useful when working with user input, as they allow for case-insensitive comparisons and text normalization. By converting user input to lowercase or uppercase, scripts can handle variations in input more effectively, reducing the risk of errors and improving overall usability. Additionally, these functions can be used to enforce specific formatting requirements or conventions within the script's logic, contributing to cleaner and more robust code. Practice session task 1. Ask user name and store input. 2. Ask user age, store and handle error. 3. Ask user for location. 4. Store all info in string.format. 5. Print info of the user. All variables and strings are arbitrary. This is a great way to emphasize the flexibility and adaptability of the code. It encourages users to experiment and customize the script according to their needs. Pause the video and take your time to solve the task. Here is my solution. Let's break down the script step by step. Ask user for their name and store the input. The io.write function prompts the user to enter their name. The io.read function reads the user's input from the console. String.upper is used to convert the user's input to uppercase, ensuring consistency in the output. The local keyword declares a local variable name to store the user's name. Ask user for their age and handle errors. Similar to the previous step, the script prompts the user to enter their age using io.write. io.read reads the input, which is then converted to a number using tonumber and stored in the variable age. An if statement checks if the entered age is not a valid number, indicating invalid input. If the age is invalid, the script prints an error message, invalid input, and exits using return, terminating the script. Ask user for their country. The script prompts the user to enter their country using io.write. io.read reads the input and string.upper converts it to uppercase for consistency. The country name is stored in the variable country. Store user information using string.format. String.format is used to create a formatted string containing the user's information. Placeholders %s and %d are used to insert the values of name, age, and country into the formatted string. The formatted string is stored in the variable info. %s is a placeholder used in string formatting to represent a string value. It is replaced with the corresponding string argument when using string.format. %d is a placeholder used to represent a decimal, integer, value. It is replaced with the corresponding numeric argument when using string.format. In the context of the script, %s is used to represent the name and country, which are string values. %d is used to represent the age, which is a decimal, integer, value. These placeholders allow for dynamic insertion of values into formatted strings, making it easy to create structured and readable output. User information. The script prints the user's information stored in the info variable using print. Overall, this script prompts the user to enter their name, age, and country, handles errors for invalid age input, formats the user's information, and prints it to the console. Test the script yourself, you'll gain hands-on experience and a deeper understanding of how it works. Don't hesitate to experiment and explore different possibilities to enhance your Lua programming skills. At this tutorial we will see the use of standard placeholders used in Lua's string.format function. %c represents a single character corresponding to the given ASCII value. ASCII, it is short for American Standard Code for Information Interchange, is the most common character encoding format for text data in computers and on the Internet. In standard ASCII encoded data, there are unique values for 128 alphabetic, numeric, or special additional characters and control codes. A signed decimal integer is a whole number that can be positive, negative, or zero. In Lua, %d is used as a placeholder for signed decimal integers when formatting strings with string.format. This means that when you use %d in string.format, it expects to replace that placeholder with a signed decimal integer value. For example, string.format, my age is %d, 25, would result in the string my age is 25. If you used a negative number like -10, it would also work. A floating point number in exponential notation, also known as scientific notation, is a way to represent numbers as a coefficient multiplied by a power of 10. In Lua, the placeholder %e or %upper e is used in string.format to format floating point numbers in exponential notation. For example, %lower e displays the number in lowercase exponential notation, while %upper e displays it in uppercase. This notation is commonly used for very large or very small numbers to make them more compact and easier to read. A floating point number in decimal notation is a way to represent real numbers, including both integers and fractions, in computer programming. In Lua, floating point numbers are typically represented using the %f placeholder in string.format. For example, %f is used to format a floating point number in decimal notation. It displays the number as a fixed point decimal number with optional fractional digits. %g placeholder in string.format is used to format a number in a more compact way compared to %e and %f. It automatically chooses between %e and %f representations based on the magnitude of the number being formatted. If the number is large or small enough to be better represented in exponential notation, %g will use %e, otherwise, it will use %f for decimal notation. An unsigned octal integer is a number represented in base 8 notation without any sign, positive or negative. In Lua's string.format function, the %o placeholder is used to format integers as unsigned octal numbers. In this example, the decimal number 255 is formatted as an unsigned octal integer, resulting in the octal representation 377. %s in Lua's string.format function represents a placeholder for a string. It doesn't inherently represent a string itself, rather, it's a formatting specifier used to insert a string value into a formatted string. In this example, %s is used to insert the string value stored in the string_val variable into the formatted string. In Lua's string.format function, %u represents a placeholder for an unsigned decimal integer. This specifier is used to format integers without a sign, positive or negative. It is commonly used when you know the value will always be positive. In this example, %u is used to insert the unsigned decimal integer value stored in the unsigned_int variable into the formatted string. An unsigned hexadecimal integer is a number expressed in the base 16 numbering system, using the digits from 0 to 9 and the letters from A to F to represent values from 0 to 15. In lieu of string formatting, %x represents an unsigned hexadecimal integer placeholder. This means it expects a number in hexadecimal format, which does not include a sign, positive or negative. For example, 0xFF represents the hexadecimal value for 255 in decimal. You can use both uppercase and lowercase letters when representing hexadecimal numbers. However, 0xUpperFF and 0xLowerFF both represent the same hexadecimal value for 255 in decimal. The double % sign represents a literal % sign in lieu of string format function. These placeholders allow you to format different types of data within a string, including integers, floating point numbers, strings, and more. Understanding and using these placeholders effectively can greatly enhance your ability to format output in lieu of scripts. In this tutorial, we'll practice using the length operator, hashtag, and the string.rep function to manipulate strings. We'll start by understanding how to use the length operator to determine the length of a string. Then, we'll explore how to use string.rep to repeat characters and create masked strings, such as masking passwords with asterisks. First, ask for password. The script prompts the user to enter their password using io.write password. io.read reads the input from the user and stores it in the variable password. Then we will calculate password length. The script calculates the length of the password using hashtag password and stores it in the variable password_length. In Lua, the hashtag symbol is called the length operator. It is used to obtain the length of a string or the number of elements in a table. Here's how it works. With strings, when applied to a string, hashtag returns the length of the string, which is the number of characters in the string. Example, a string hello would set length to 5 because hello has 5 characters. With tables, when applied to a table, hashtag returns the number of elements in the sequence part of the table, the part with integer keys starting from 1. Example, local table equals 10, 20, 30, 40, local count equals hashtag table would set count to 4, because there are 4 elements in the table. Notes: the length operator only works reliably on sequences with consecutive integer keys starting from 1. It does not count elements with nil values or elements with non-integer keys. Next step, we will check password length. Using if and Elseif statements, the script checks if the password is too long, more than or equal to 10 characters, or too short, less than or equal to 4 characters. If the password is too long, it prints your password is too long. If the password is too short, it prints your password is too short. Now we will mask the password. If the password is neither too long nor too short, it proceeds to mask the password with asterisks. It uses string.rep, in quotes asterisk, comma password underscore length, to create a string of asterisks with the same length as the password and stores it in masked underscore password. String.rep function is particularly useful for creating patterns, generating strings with repeated characters, or masking sensitive information like passwords with asterisks. It's a handy tool for various string manipulation tasks, offering simplicity and efficiency in repetitive string generation. At the end, we will display the masked password. Finally, it prints the masked password to the user using print masked password \n concatenation masked underscore password. The \n adds a new line for better formatting. In conclusion, this tutorial covered the use of the length operator, hashtag, and the string.rep function in Lua. We learned how to determine the length of a string using hashtag, which is useful for various tasks such as input validation, password masking, and string manipulation. Additionally, we explored how to mask a password by repeating the asterisk character using string.rep, providing a simple yet effective way to enhance security in user interactions. By practicing with these fundamental string operations, you've gained valuable insights into Lua's string manipulation capabilities, which will be beneficial as you continue to explore and develop Lua scripts. Keep experimenting and building upon these foundational concepts to unlock even more possibilities in your Lua programming journey. In this tutorial, we'll delve into the fascinating world of string manipulation in Lua. We'll explore how to reverse strings, encrypt messages, and more using simple yet powerful string functions. Get ready to unlock the secrets of strings and elevate your Lua programming skills. First, we will ask for input, prompts the user to enter a secret message and store the message in a variable. Next, we will do a length check, ensures the message length is within an acceptable range, between 5 and 50 characters. String.len is a function in Lua used to get the length of a string. It takes a string as its argument and returns the number of characters in that string. In the script, string.len is used to ensure that the length of the user's input falls within an acceptable range, between 5 and 50 characters. This helps validate the input before proceeding with the encryption process. Shortening code can make it more concise and easier to read, but it's important to balance brevity with readability, especially for learners. In this tutorial, using string.len explicitly helps reinforce the concept and makes the code more accessible for beginners. As learners become more comfortable with Lua, they can explore more concise coding practices. It's crucial to continuously check code for errors while writing it. This practice helps catch mistakes early on and ensures a smoother coding experience overall. Our next step will be to reverse the message. Reverses the input message using the string.reverse function to create a mirror image of the original message. This way we add an extra layer of complexity to the encryption process. It can make the encrypted message less predictable and more secure, as it changes the order of characters before encryption. Additionally, reversing the message can enhance the visual appeal and intrigue of the encryption process for learners. Encrypt the message iterates over each character of the reversed message using a for loop. At each iteration, retrieves the ASCII value of the character using string.byte and appends it to the encrypted message string. The for loop is a fundamental control structure in programming used for iterating over a sequence of elements. In this context, we use it to iterate over each character in the reversed message and convert it to its ASCII representation using string.byte. The loop simplifies the process of accessing each character in the string and performing the encryption operation on it. In computer science and programming, an index typically refers to the position or location of an element within a data structure, such as an array, string, or list. In Lua, strings are indexed starting from 1, unlike some other programming languages where indexing starts from 0. String indexing: in Lua, you can access individual characters of a string using their index positions. For example, in the string hello, the character h is at index 1, e is at index 2, and so on. The usage in our script. In the script, the variable I is used as an index to iterate over each character of the message string. Inside the loop, message sub I is used to extract the character at the current index I. Dynamic access. By dynamically changing the index I within the loop, you can access each character of the string sequentially, allowing you to perform operations on individual characters. In Lua, the string.sub function is used to extract a substring from a given string. The syntax message sub I, means to extract a substring from the message string, starting at index I and ending at index I. In other words, message sub I extracts a single character from the message string at the position specified by the variable I. The I variable is typically used to iterate over each character of the string in a loop. Our last step, we will print encrypted message, displays the encrypted message, showing the ASCII values of each character. Note: in that case, our intention is to print the encrypted message only once after the loop has finished processing the entire message. You should place the print statement outside of the loop block. With this arrangement, the loop iterates over each character of the message, encrypts it, and appends it to the encrypted message string. After the loop finishes processing the entire message, the print statement executes once to display the encrypted message. Second note: by adding a space after each byte value in the encrypted message variable, you ensure that each value is separated by a space when it's printed. This makes the output more readable and easier to interpret. Without the space, the byte values would be concatenated together without any separation, making it difficult to distinguish between them. In this tutorial, the primary focus is on understanding and manipulating strings using string functions like string.reverse and string.byte. While the script does utilize a for loop to encrypt the message, the emphasis is not on the loop itself but rather on how it interacts with string operations. It's important to note that loops, including for loops, are a fundamental concept in programming, and they will be covered in more detail in future tutorials. By keeping the focus on strings in this tutorial, we provide a solid foundation for understanding more complex concepts like loops in subsequent lessons. In the next tutorial, we'll decrypt the encrypted message generated in this tutorial. We'll continue to explore string manipulation techniques and delve into the process of reversing the encryption to reveal the original message. This will provide a comprehensive understanding of both encryption and decryption processes, building upon the concepts introduced in this tutorial. Welcome back to our Lua Basics tutorial series. In our previous tutorial, we covered the encryption of messages using string manipulation functions. At this tutorial, we'll pick up right where we left off and delve into decrypting those encrypted messages. So, if you're ready, let's dive in and unlock the secrets hidden within our encrypted messages. In the previous tutorial, we had separate blocks of code to check if the message length exceeded certain limits. To make our code shorter, we will combine these blocks using the logical operator OR. This allows us to check both conditions in a single if statement, reducing redundancy and making our code more concise. After making changes to our code, it's important to check it thoroughly to ensure everything is correct. We've verified and optimized our encryption code. We're ready to proceed with the decryption block. This block will reverse the process of encryption to restore the original message. We'll create a variable decrypted message and initialize it as an empty string. This variable will store the decrypted message. Next we will use once again a for loop, but this time with gmatch. We'll use a for loop combined with the gmatch function to iterate over the encrypted message and extract each numerical value representing a character. The %d+ pattern in gmatch matches one or more digits in the string. Word is not a reserved keyword or predefined variable. It's a generic variable name commonly used to represent a single element or component of a text or string, particularly in contexts where the text is being processed or analyzed. In the decryption block of our script, word is used as the loop variable in the for loop that iterates over the numerical values extracted from the encrypted message. Each iteration, word represents a single numerical value, which is then converted back to its corresponding character. Now we will proceed our string conversion. Within the loop, we'll convert each numerical value back to its corresponding character using string.char function and inside using tonumber function with argument word. The tonumber function converts the numerical string to a number, and string.char function converts the number to its ASCII character representation. Each decrypted character will be concatenated to the decrypted message variable. Finally, we'll print the decrypted message to the console. The decryption block will be able to reverse the encryption process and retrieve the original message, completing the encryption and decryption cycle. Now we'll reverse the decrypted message using the string.reverse function. This step restores the original message to its initial order, completing the entire process. Gmatch is a method available on string objects. It stands for global match and is used to iterate over all occurrences of a pattern in a string. In this context, encrypted message is a string variable containing the encrypted message, which consists of numbers separated by spaces. The pattern %d plus passed to gmatch specifies that we're looking for one or more digits in the string. So, %d plus matches any sequence of one or more consecutive digits. When gmatch is called with %d plus as its argument, it returns an iterator function. This iterator function, when called repeatedly in a loop, returns each occurrence of the pattern found in encrypted message. The for loop iterates over each match found by the gmatch function. In each iteration, word represents one match, which is a sequence of digits from the encrypted message. Overall, encrypted message, match %d plus allows us to extract each individual number from the encrypted message by iterating over all sequences of consecutive digits. Let's delve deeper into decrypted message assigned to decrypted message :string.char to number word. Word, this variable represents each match found by the gmatch function. These matches are sequences of digits from the encrypted message. TONumber converts the string representation of a number into an actual numerical value. For example, if word is 65 in quotes, TONumber, word, would return the number 65. The string.char function takes numerical ASCII values as arguments and returns the corresponding characters. For instance, string.char, 65, returns the character uppercase letter A as 65 is the ASCII value for the uppercase letter A. Lua uses the concatenation operator ... to concatenate, or join together, strings. In this context, decrypted message. String.char, TONumber, word, appends the character obtained from string.char, TONumber, word, to the existing decrypted message string. By repeatedly performing decrypted message assigned to decrypted message :string.char, TONumber, word, within the loop, each numerical value from the encrypted message is converted into its corresponding character and added to decrypted message. This process effectively decrypts the message, converting it from a sequence of ASCII values back into readable text. By mastering functions like string.reverse, string.byte, and string.char, we've unlocked powerful tools for manipulating and transforming text data. Remember to practice and experiment with these functions to deepen your understanding and proficiency. As we progress in our Lua journey, we'll continue to explore more string functions and their effects, unraveling the intricacies of text processing and manipulation. Stay tuned for our next tutorial, where we'll dive deeper into the fascinating world of Lua programming. Keep coding and exploring, and let your creativity flourish. Practice session task. 1. Create a variable and assign it a value. 2. Use type to determine the type of the variable. 3. Extract alphanumeric character from the password variable with string.match. 4. Display the extracted content. Pause the video and take your time to find a solution. Here is my solution. First, we will declare a variable named password and assign it the value brave. This variable will hold our password. Next, we will use the type function to check the type of the password variable. The type function returns the data type of a value. In this case, we're checking if the type of password is not equal to nil. If it's not nil, it means the variable exists. When programming, developers often use variable names that are intuitive and descriptive of the data they represent. For example, when storing a password, common variable names might include password, pass, or key. This convention makes the code easier to understand and maintain for both the original developer and others who may work with the code later. In the context of searching for a password stored in a script, it's reasonable to assume that the developer has followed this convention and named the variable holding the password using one of these common names. Therefore, when attempting to locate the password within the script, searching for variables named password, pass, or key is a logical and efficient strategy. This approach maximizes the likelihood of successfully identifying the variable holding the password. Next, we will proceed to pattern matching. Here, we will use string.match function to extract alphanumeric characters from the password variable. The %w plus pattern matches one or more alphanumeric characters. Pattern matching in programming involves searching for specific patterns or sequences within a string or data structure. In Lua, pattern matching is often done using pattern strings, which are similar to regular expressions but have a simpler syntax. It allows you to find and extract specific substrings based on predefined patterns or rules. This can be particularly useful for tasks such as parsing text, validating input, or extracting specific information from strings. In the context of your tutorial, pattern matching will be used to search for specific keywords like password, pass, or key within a string to identify variables that might store passwords. Finally, we print the extracted content of the password variable using print. We display the label. The password is followed by the extracted content. In this solution, it's essential to highlight that everything presented is arbitrary, and users can adapt the code to fit their specific needs. Variable names, data types, and patterns can vary based on the user's preferences and the requirements of their project. By understanding the underlying concepts and techniques demonstrated, users can apply them creatively and effectively in their own programming endeavors. In this tutorial, we will delve into the realm of text manipulation in Lua. By combining the power of loops and string functions, we'll explore how to search for specific words within a text and replace them with others. This exercise offers valuable insights into how to efficiently handle and transform text data in Lua scripts. Let's dive in and uncover the intricacies of text manipulation with Lua. The global variable message is assigned the string neo follow the white rabbit. This line initializes the message we'll work with. The print function is used to display the original message stored in the variable message. The string.find function is used to search for the word rabbit within the message. It returns the starting and ending positions of the word rabbit if found. The if statement checks if the start position variable is truthy, indicating that the word rabbit was found. If found, it prints the position where the word rabbit starts. If not found, it prints that the word was not found. In Lua, when using the string.find function to search for a substring within a string, the return position represents the index of the first character of the found substring within the entire string. This means that the position returned is the index of the first letter of the word being searched for. So, when we get the position of rabbit, it indicates the position of the first letter R in the word rabbit within the original message string. If you start the search from abbot instead of rabbit, the position returned by string.find will change accordingly. The string.gsub function is used to replace all occurrences of the word rabbit with fox in the message. It returns a modified version of the message with the replacements. The modified message, with rabbit replaced by fox, is printed using the print function. When we use string.gsub to replace a substring within a string, Lua creates a new string with the replacements made, leaving the original string unchanged. This is because strings in Lua are immutable, meaning they cannot be modified directly. Instead, operations like replacement result in the creation of a new string object with the desired changes applied. So, when we replace a substring in a string using string.gsub, we receive a new string containing the modifications while keeping the original string intact. This script showcases the versatility of Lua's string manipulation capabilities. By utilizing functions like string.find and string.gsub, we can search for specific words within a string and replace them with ease. Understanding these string manipulation functions opens up a world of possibilities for text processing and data manipulation in Lua. With practice and experimentation, you'll become proficient at harnessing the power of strings in your Lua scripts. Keep exploring and refining your skills. Loops are essential in programming for repeating tasks, and the for loop is a powerful tool for iterating over a range of values. We'll start with a basic example to illustrate how the for loop works and gradually explore its various features and applications. Let's compare the manual printing of numbers from 1 to 10 with using a for loop. With manual printing approach, we explicitly print each number from 1 to 10. This method can be tedious and repetitive, especially for larger ranges of numbers. On the other hand, the for loop provides a more efficient and concise way to achieve the same result. By specifying the range of values, 1 to 10, and the variable, I, to iterate over that range, we can print each number using a single loop iteration. This approach is more scalable and easier to maintain, especially when dealing with larger ranges or dynamic data. Printing 1 million numbers individually without a loop would be impractical and inefficient. It would require writing out each number manually, resulting in a massive amount of redundant code and significantly increasing the risk of errors. By contrast, using a loop allows us to achieve the same outcome with much less code and effort. A loop iterates over the numbers sequentially, printing each one automatically according to the loop's conditions. This approach is not only more concise but also more scalable and maintainable, making it the preferred method for tasks involving large numbers of iterations. By default, the increment of the loop is by 1. While it's not necessary to explicitly specify an increment of 1 in the loop statement, doing so can enhance code readability, making it clear that the loop variable is being incremented by 1 with each iteration. This explicit notation can aid in understanding the loop's behavior, especially in more complex code where the increment might not be immediately obvious. We can augment the loop by changing the increment value, which determines how much the loop variable increases or decreases with each iteration. For example, instead of incrementing by 1 each time, we can increment by 2, 3, 4, or any other desired value. This allows us to skip numbers or print them in a different pattern. It provides flexibility and control over the loop's behavior, enabling us to achieve various outcomes efficiently. I is often used as a shorthand for index in programming, especially in contexts like loops where it represents a position or iteration count. While it's not a strict rule, using I as a loop counter is a common convention in many programming languages, including Lua. The variable index in a for loop is commonly used as the loop counter. It represents the current iteration of the loop. In a typical for loop structure like for index equals 1, 100, do index starts at the initial value, in this case, 1, and the loop executes until index reaches the end value, in this case, 100, incrementing index by 1 with each iteration. Inside the loop block, index can be used to access elements or perform actions based on the current iteration number. It's a temporary variable that exists only within the scope of the loop and is automatically increment or decrement based on the loop's parameters. In practical scenarios, such as password cracking or searching through large datasets, the break statement is invaluable for optimizing performance and ensuring timely execution. It's a powerful tool for controlling the flow of loops and enhancing the efficiency of algorithms. By incorporating the explanation of the break statement, learners can better understand its significance in controlling loop execution and improving code efficiency. In this tutorial, we'll explore a basic Lua script that attempts to guess a password using a brute force technique. Brute force attacks involve systematically checking all possible combinations until the correct one is found. First, we will set a local variable password to the target password we want to guess. Brute force attacks on passwords can be time-consuming, especially for longer passwords or larger search spaces. Consider whether iterating through all possible combinations is necessary or practical. Password guessing. Instead of brute force, it might be better to use more targeted password guessing techniques based on known information or common password patterns. Next, we will simulate a brute force loop. We will iterate from 1 to 9999, converting each number to a string and comparing it with the target password. With this line, we will effectively convert the numeric loop index I into a string and assigns it to the variable I string. This conversion allows us to perform string-based operations or comparisons with the loop index I, which was originally a numeric value. Inside the loop, we will check if the current string matches the password. If it does, we print a success message and terminate the loop. After the break statement, we will print the current guess at each iteration to track the progress of the brute force attack. You can use this script in any Lua environment to simulate a basic brute force attack on a password. However, please use it responsibly and only on systems where you have explicit permission to test security vulnerabilities. Brute force attacks are just one of many techniques used by attackers to compromise passwords. Understanding how they work can help you better defend against them and design more secure systems. Conclusion: the break statement in Lua is a powerful tool for controlling the flow of loops. It allows you to exit a loop prematurely based on a specific condition, improving the efficiency and readability of your code. By understanding how and when to use break, you can write more concise and effective Lua scripts. This tutorial introduces the Caesar cipher, an ancient encryption technique dating back to Julius Caesar's time. Through a simple script, users are prompted to input a message and specify a shift value, determining how many positions each letter in the message should be shifted down the alphabet. The script demonstrates the algorithm's implementation in Lua, using string manipulation and ASCII character codes to achieve encryption. By exploring the Caesar cipher, learners gain insight into fundamental encryption principles and the historical significance of cryptography in securing sensitive information. First, we will prompt the user to enter a message and a shift value using IOWrite and IOWread functions. Next, we will convert the input shift value from a string to a number using tonumber function. Prompting for the shift value in a Caesar cipher allows users to customize the level of encryption applied to their message. The shift value determines how much each letter in the message is shifted down the alphabet, thus altering the encryption. By prompting for the shift, users can choose the level of security for their message. Using tonumber is necessary because IOWread returns a string value by default. However, for numerical operations, such as determining the shift value, we need to convert this string to a numerical data type. Tonumber accomplishes this conversion by converting the string input into a number, allowing us to perform mathematical operations on I. We will initialize an empty string in the variable encrypt to store the encrypted message. 4. This keyword signals the start of a loop. I equals 1, we initialize a loop control variable I with the value 1. This variable will be used to track the current iteration of the loop. Hashtag message. The hashtag it is the unary operator in Lua and calculates the length of the message string. So unary operator in message returns the number of characters in the message string. Do marks the beginning of the block of code to be executed in each iteration of the loop. So, the loop iterates from 1 to the length of the message string, unary operator message, inclusive. In each iteration, the loop control variable I takes on the values 1, 2, 3, up to the length of the message string. The sub function is used to extract a substring from the message string. It takes two arguments, the starting index and the ending index. In this case, both the starting and ending indices are I, which means we're extracting a single character from the message string at index I. So, in each iteration of the loop, the shift variable will contain the character at index I of the message string. This allows us to process each character of the message string one by one within the loop. If cipher greater or equal to A and cipher less or equal to Z, then this line checks if the character cipher is a lowercase letter. Cipher greater or equal to A checks if the character cipher comes after or is equal to the lowercase letter A in the ASCII table. Cipher less or equal to Z checks if the character cipher comes before or is equal to the lowercase letter Z in the ASCII table. Together, this condition ensures that cipher is a lowercase letter. Cipher byte. This method returns the ASCII value of the character cipher. Cipher byte -97 plus shift %26. This part performs the encryption by shifting the ASCII value of the character cipher. Cipher byte -97, subtracting 97 normalizes the ASCII value of cipher to the range 0 to 25, assuming cipher is a lowercase letter. For example, if cipher is A, its ASCII value is 97, so cipher byte -97 evaluates to 0. Shift. This is the amount by which the characters are shifted for encryption. %26. This ensures that the result stays within the range 0 to 25, which is important for wrapping around the alphabet. For example, if shift is 3 and cipher is C, ASCII value 122, the result of 122 to 97 plus 3 would be 28. But %26 ensures it wraps around to 2, corresponding to B. String.char. This method converts a number to its corresponding ASCII character. The result of the encryption, after the modulo operation, is added to 97 again to bring it back to the ASCII range of lowercase letters. For example, if the result of the encryption modulo operation is 2, adding 97 will give 99, which corresponds to the ASCII value of C. In summary, this line takes a character cipher, shifts it by the value of shift, ensures the result stays within the range of lowercase letters, and converts it back to a character. Next, we will repeat the process for uppercase letters using an Elseif statement. Similar to the lowercase, this time we will add 65 to the result to bring it back to the ASCII range of uppercase letters, and then convert it back to a character. ASCII lowercase a is 97. ASCII uppercase a is 65. The line encrypt equals encrypt double dot cipher is used to build the encrypted message gradually as we iterate through the characters of the original message. Here's what it does. Encrypt. This variable holds the encrypted message. Double dot. This is the concatenation operator in Lua. It appends the value of cipher to the current value of encrypt. Cipher. This represents the character that has been encrypted in the current iteration of the loop. So, each time we encrypt a character, cipher, we append it to the encrypt variable, gradually building up the encrypted message character by character. In summary, encrypt equals encrypt double dot cipher ensures that each encrypted character is added to the encrypted message, ultimately forming the complete encrypted message. The last line will do print the encrypted message to the console. In Lua, the string.sub function is used to extract a substring from a given string. The syntax for string.sub is string.sub, string, start, end, where string is the original string, start is the starting index of the substring, and end is the ending index of the substring. If end is not provided, the substring will extend to the end of the original string. In our example, message:sub I, is equivalent to string.sub message, I. It extracts a single character from the message string at the position specified by I. In Lua, the colon operator is a syntactic sugar for method calls. When you see object:"method, args, it's equivalent to object.method, object,"args. This syntactic sugar simplifies the code and makes it more readable, especially when working with object-oriented code. In the context of string manipulation, using the colon syntax with string methods is common. In this example, the colon syntax simplifies the method call by automatically passing string.str as the first argument to the sub method. In conclusion, we've explored the convenience of using the colon operator with string methods in Lua. This syntax streamlines method calls by automatically passing the string itself as the first argument. By leveraging this approach, our code becomes more concise and readable. In this tutorial, we will decrypt our Caesar cipher by reversing the encryption process. We're shifting each character in the encrypted message back by the same amount to reveal the original message. By subtracting the shift value from the ASCII value of each character, we will effectively undoing the encryption and recovering the plain text message. The first step in decrypting the Caesar cipher is to loop through each character in the encrypted message. We use a for loop to iterate over the characters in the encrypted string. Within the loop, we extract each character one by one using the string.sub function. This allows us to examine each character individually and perform decryption operations on them. In the next step, we will use if statements to differentiate between lowercase and uppercase letters in the encrypted message. We will check each character to determine if it falls within the range of lowercase or uppercase ASCII values. If the character is lowercase, we will perform decryption operations specific to lowercase letters. Similarly, if the character is uppercase, we will apply decryption operations tailored to uppercase letters. This allows us to handle both types of characters appropriately during the decryption process. Step-by-step explanation. String.byte function is used to convert each character of the string to its corresponding ASCII value. This allows us to perform arithmetic operations on the ASCII values. The shift value is subtracted from the ASCII value of each character. This effectively shifts the characters forward or backward in the ASCII sequence based on the value of the shift. The modulo operation %26 ensures that the shifted ASCII value remains within the range of alphabetical characters, from lowercase a to lowercase c or from uppercase a to uppercase c. For example, if the shift value is 1 and the original character is lowercase c, ASCII value 122, subtracting 1 would result in 121, which is outside the range of lowercase letters. However, taking the modulo 26 of 121 results in 25, which corresponds to the ASCII value of y, ensuring that the shifted character remains valid. Finally, string.char function is used to convert the shifted ASCII values back to characters. This reconstructs the encrypted or decrypted message with the shifted characters. This process allows for the encryption and decryption of messages using the Caesar cipher technique. In these lines, we will append each decrypted character, cipher, to the decrypt string using the concatenation operator . This will build up the decrypted message character by character as we loop through the encrypted message. Once the loop is complete, we will print out the entire decrypted message to reveal the original plain text. In wrapping up our exploration of the Caesar cipher, we've gained a fundamental understanding of encryption and decryption techniques using Lua. By delving into the mechanics of shifting characters and manipulating ASCII values, we've unlocked the secrets of this ancient encryption method. Armed with this knowledge, you're now equipped to dive deeper into the world of cryptography and explore more advanced encryption algorithms. Keep experimenting, stay curious, and continue sharpening your skills in the fascinating realm of information security. Lua provides a built-in function called math.random for generating pseudorandom numbers. This function is commonly used in game development, simulations, and other scenarios where randomness is required. Math.random generates pseudorandom numbers, meaning the sequence of numbers it produces appears random but is actually deterministic. The sequence depends on an initial seed value. By default, calling math.random with no arguments returns a real number between 0, inclusive, and 1, exclusive. You can specify a range for the random numbers using 1 or 2 arguments. When called with one argument. Example. Math.random 100, it returns an integer between 1 and 100. When called with 2 arguments. Example. Math.random 50, 100, it returns an integer between 50 and 100. Math.randomseed is a function in Lua used to set the seed for Lua's pseudorandom number generator. It is used to set the initial seed value for Lua's random number generator. By setting the seed, you can ensure that the sequence of random numbers generated is deterministic and reproducible. If you want to generate the same sequence of random numbers each time you run your program, you can set a fixed seed using math.randomseed. The sequence of numbers depends on the initial seed value set by math.randomseed. If you set the same seed, you will always get the same sequence of random numbers. Math.randomseed takes an optional integer argument representing the seed value. If no argument is provided, Lua uses a default seed based on the current time and date. You typically call math.randomseed before using math.random to ensure consistent behavior. Math.random is the function used to actually generate random numbers. Math.randomseed sets the initial seed for the random number generator. Math.randomseed is not a replacement for math.random, but rather a companion function used to control the behavior of math.random. In summary, math.randomseed is used to control the randomness of math.random by setting the initial seed value, allowing for reproducible sequences of random numbers. Practice session task. 1. Set the random seed to the current time. 2. Generate and print a random password. 3. Set a variable. 4. Use a for loop to brute force the password. 5. Use an if statement. 6. Print the hacked password. 7. Use break and close. Pause the video and take your time to solve the task. Then come back to see my solution. Note: in the provided solution, the variable names are arbitrary as usual, meaning they were chosen for illustrative purposes and can be replaced with any other valid variable names. This flexibility allows you to customize your code to better suit your project's needs or personal coding style. Remember, when writing your own code, opt for variable names that are descriptive and meaningful to enhance code readability and maintainability. Math.RandomseEd can reinforce randomness by introducing more entropy into the pseudorandom number generation process. By using a changing seed, such as os.time, you ensure that each time you run your script, the sequence of pseudorandom numbers generated by math.random will be different. However, it's important to note that the quality of randomness also depends on the underlying random number generator implementation in Lua and the platform it's running on. So while setting the seed can help, it doesn't guarantee perfect randomness. os.time is a Lua function that returns the current time in seconds since the epoch. The epoch refers to a specific point in time used as a reference for timekeeping in computing systems. In Unix and POSIX systems, the epoch is defined as January 1, 1970, 0:00 Universal Time Coordinated. This moment serves as the origin from which timestamps are measured, with time increasing in seconds since the epoch. The os.time function in Lua returns the number of seconds elapsed since this epoch. It's a useful function for generating random seeds based on the current time, which can help increase the randomness of random number generation when combined with math.randomseed. Using math.random, with a range between 999 and 99999, we will generate and store each time a random password in the variable dynamic_pass. This password will be then printed to the console. Next we will set the variable brute_force, which is declared to store the hacked password, if it is found. We will start with a simplified version of the loop for clarity. However, for functionality, we will transform the traditional loop structure. This transition allows for a clearer illustration of how the loop operates in the context of brute forcing. To simulate the process of searching for an integer password, we adjusted the range values of the loop. Instead of iterating from 1 to 10 as in the simplified loop, we extended the range to cover a much larger space, from 0 to 999,999,999. This adjustment allows us to simulate the brute force process more realistically, enabling the loop to iterate through a wide range of possible password values. Next, we will use inside the loop an if statement to check if the current number matches the generated random password. By assigning hack to brute_force, we effectively capture the correct password once it's found during the brute force search. Now we will print the captured password, and after that we will use break to exit the loop, as there is no need to continue brute forcing. In wrapping up this tutorial, we've delved into the intriguing world of password brute forcing in Lua. Through the exploration of random password generation and iterative guessing, we've gained valuable insights into password security and ethical hacking practices. Remember to use these skills responsibly and always prioritize privacy and security. Loops are incredibly powerful tools in programming, allowing us to execute a block of code repeatedly in Lua. The for loop is often used when you know exactly how many times you want to repeat a block of code. It has a straightforward syntax, where you specify a starting value, an ending value, and an optional step value. Each time the loop iterates, a variable is assigned a new value within the specified range. The while loop is another fundamental concept in programming that allows us to repeat a block of code as long as a certain condition remains true. Think of it like a repeating task that continues as long as a specific condition is met. Imagine you're playing a game where you need to collect coins until you reach a certain score. You would keep collecting coins until you achieve your goal. The while loop works similarly in programming. In this example, the loop starts with I set to 1. As long as I is less than or equal to 5, the loop will continue. Inside the loop, we print the current value of I and then increment it by 1. This process repeats until I becomes greater than 5, at which point the loop terminates. The while loop is incredibly useful for scenarios where we don't know in advance how many times we need to execute a block of code, making it a valuable tool in your programming toolkit. Both the for and while loops are control structures in Lua that allow us to repeat a block of code multiple times based on certain conditions. Despite their differences in syntax and usage, they share several similarities. Both loops are used for iteration, which means they execute a block of code repeatedly until a certain condition is met. This makes them essential for automating repetitive tasks in programming. Both loops are used for iteration, which means they execute a block of code repeatedly until a certain condition is met. This makes them essential for automating repetitive tasks in programming. They rely on a condition to determine whether the loop should continue executing. In the case of the for loop, the condition is typically related to the loop variable, while the while loop evaluates an arbitrary condition. The loops offer flexibility in terms of how they control the loop execution. For example, in the for loop, you can specify the initial value, loop condition, and increment or decrement in a single line, while the while loop allows you to customize the loop condition more dynamically. Although the syntax differs, both loops allow you to increment or decrement a loop variable to control the iteration. In the for loop, this is done implicitly through the loop control expression, while in the while loop, you manually update the loop variable within the loop block. Both terminate when the loop condition evaluates to false. This ensures that the loop does not execute indefinitely, preventing potential infinite loops that could cause the program to hang or crash. Overall, while both loops have distinct syntax and use cases, they share fundamental principles and serve similar purposes in controlling the flow of program execution. In this tutorial, you will learn how to create a simple game loading script in Lua. This script will prompt you to enter a password to access the game. You'll have a limited number of attempts to enter the correct password before being locked out. Attempts. This variable is used to track the number of login attempts made by the user. It starts at 0 and increases each time the user enters an incorrect password. Max_attempts. This variable sets the maximum number of login attempts allowed. In this script, it's set to 3, meaning the user has 3 chances to enter the correct password before being locked out. Success. This variable is a Boolean flag that indicates whether the user successfully logged in. It is initially set to false and will be set to true if the user enters the correct password within the allowed number of attempts. If success remains false after all attempts, it means the user failed to log in. While attempts less than max_attempts do, this line begins a while loop that continues as long as the attempts variable is less than the max_attempts. In other words, the loop will run as long as the user has not exceeded the maximum allowed login attempts. IOWrite function displays a prompt asking the user to enter their password. This function is used to print the prompt to the console without adding a new line character, allowing the user to input their password on the same line. Local password reads the user's input from the console and stores it in the password variable. The IORead function waits for the user to input text and press enter before proceeding. The inputted text is then stored in the password variable for further processing. If password equal to 1234, then this line checks if the password variable matches the correct password, which in this case is 1234. If the user enters the correct password, the code inside the if block will execute. This line sets the success variable to true, indicating that the correct password was entered. This variable will be used later to determine whether the game should be loaded. After successfully entering the correct password, the break statement is used to exit the while loop. This prevents the loop from continuing to prompt the user for their password. If the user enters an incorrect password, the code inside the else block will execute. This line increments the attempts counter by 1, tracking the number of unsuccessful login attempts. This next line calculates and prints the remaining attempts by subtracting the current number of attempts from the maximum allowed attempts. It informs the user of how many attempts they have left before being locked out. Overall, the while loop ensures that the user is repeatedly prompted for their password until a valid input is received or the maximum number of attempts is exceeded. After the while loop completes, the script checks the value of the success variable to determine whether the user successfully logged in or not. If success is true, it means that the correct password was entered within the allowed number of attempts. In this case, the script prints password correct, indicating that the user successfully logged in. If success is false, it means that either the user exceeded the maximum number of attempts or entered the wrong password each time. In this case, the script prints user banned, indicating that the user is not allowed access to the game. The success variable is used to keep track of whether the user successfully logged in during the while loop. It is initially set to false and only set to true if the correct password is entered. This variable helps control the flow of the script and determines the final outcome based on the user's login attempts. The while loop serves as the guardian at the gates of the game, standing sentinel against unauthorized entry. Like a mystical barrier, it enforces the rules of entry, allowing only those who possess the secret password to pass through its ethereal threshold. With each iteration of the loop, the seeker is presented with a riddle: please enter your password. This enigmatic prompt beckons the user to whisper the correct incantation, testing their knowledge and resolve. As the seeker utters their chosen phrase, the if statements act as spectral guides, discerning the truth from deception. If the uttered words align with the hidden truth, the gates swing open, granting passage into the realm of the game. But beware, for with each failed attempt, the guardian grows stronger, its resolve unyielding. The seeker's attempts are counted, the sands of time slipping away with each incorrect invocation. Finally, as the loop concludes its mystic dance, the success variable reveals the fate of the seeker. Will they emerge victorious, their spirit aligned with the secrets of the game? Or will they be cast aside, their journey halted by the unforgiving hand of fate? In the end, the while loop serves as both gatekeeper and guide, testing the seeker's mettle and determining their destiny in the ever-shifting sands of the digital realm. We have already used os.time and math.random functions in previous tutorials, so let's recap. Math.randomseed function is used to initialize the random number generator with a seed value. We typically use os.time to generate a seed value based on the current time, ensuring that each time we run the program, we get a different sequence of random numbers. Once the random number generator is seeded, we can use math.random to generate random numbers. This function can be called with or without arguments. Without arguments, it returns a pseudorandom floating point number in the range between 0 and 1, excluding 1. With arguments, it returns an integer value within the specified range. os.time function returns the current time in seconds since the Unix epoch, January 1, 1970. It's often used in combination with math.randomseed to generate a seed value for the random number generator. os.date is a function in Lua used to retrieve the current date and time or format a given date and time into a string. It belongs to the OS module, which provides functions related to operating system operations. You can specify a format string to customize the output. This format string consists of various placeholders representing different components of the date and time. For example, %uppercase y represents the year, %lowercase m represents the month, %lowercase d represents the day, and so on. Besides the current date and time, os.date can also format specific dates and times. By providing a Unix timestamp as a second argument, you can format any date and time, not just the current one. os.date is a handy tool for tasks involving date and time manipulation, such as logging, displaying timestamps in user interfaces, or generating time-sensitive content. Its flexibility in formatting allows developers to tailor date and time representations to their specific needs. When called without any arguments, os.date returns a string representing the current date and time. The format of the string is system-dependent, typically following the ISO 8601 standard. It can be used to set expiration dates or time limitations in scripts. For example, you can compare the current date with a predetermined expiration date to determine if a license or subscription has expired, or if a time-limited trial period has elapsed. Overall, os.date is a versatile function that allows you to work with dates and times in lieu of scripts, enabling you to perform various operations such as formatting, comparison, and implementing time-based logic. Whether it's displaying the current date and time, comparing dates for logical operations, or implementing sophisticated expiration logic, os.date empowers creators to bring their scripts to life with precision and finesse. Practice session task. Define the message and encryption key. Encrypt the message. Read the current date. Check if the current date is before the target date. Decrypt the message. And print the decrypted message. Note: as usual, the used variables are arbitrary, and I will use the concept of the Caesar cipher for encryption in this tutorial. Pause the video and take your time to solve the task, then come back to see my solution. We start by defining the plain text message that we want to encrypt. Here, the message is: "This is a message in a bottle." Next, we set the encryption key. The key determines how many positions each character in the message will be shifted in the Caesar cipher encryption process. We define our encryption variable with an empty string. Then iterate over each character in the plain text message using a loop. For each character, we check if it is a lowercase letter. If all characters are lowercase, we apply the Caesar cipher encryption by shifting the character's Unicode value by the key amount. We use modulo 26 to wrap around the alphabet if needed. In the script, the value 97 is used as a reference point in ASCII encoding. In the encoding, the lowercase alphabet characters from A to Z are represented by consecutive integers starting from 97 for A, 98 for B, and so on, up to 122 for Z. In this line, cipher byte -97 converts the ASCII value of the character cipher to a value between 0 and 25 by subtracting 97, as explained earlier. Then, plus key adds the encryption key value to this result. Adding 97 back at the end of the expression ensures that the resulting value is shifted back into the range of ASCII values for lowercase alphabets. This step is crucial for correctly mapping the encrypted characters back to their respective alphabetical positions in the ASCII table. The line encrypted_message equals encrypted_message double-dot-cipher appends each encrypted character cipher to the encrypted_message string. This accumulates the encrypted characters one by one, effectively building the entire encrypted message. We use the os.date function to get the current date in the format year, month, day. Only integers. The current date is stored in the current_date variable. We compared the current_date variable with the target date 20240301. Means, March 1st, 2024. If the current date is before the target date, we print a message indicating that the message is still locked. Otherwise, we proceed to decrypt the message. If the current date is on or after the target date, we proceed to decrypt the message. The decryption reversing the process in a similar way. Iterate over each character in the encrypted_message using a loop. For each character, check if it is a lowercase letter. If it is, apply the Caesar cipher decryption by shifting the character's Unicode value back by the key amount. Then append the decrypted character to the decrypted_message variable. Reminder: The encrypted message, subit, is a form of syntactic sugar in Lua. It's a convenient way to call methods on objects, making the code cleaner and more readable. The line encrypted message operator sub I, is a shorthand syntax in Lua that allows us to call the sub function on the encrypted message string object. This function extracts a substring from the encrypted message string, starting at index I and ending at index I. Essentially, it retrieves the character at position I within the encrypted message string. This shorthand notation is equivalent to calling string.sub, encrypted message I. Once the decryption is complete, print the decrypted message to the console. This script demonstrates a basic implementation of encryption and decryption using the Caesar cipher, with the added functionality of checking the current date to determine whether the message should be decrypted. As the sun sets on our tutorial's journey, the message, once encrypted, finds its key. With patience and time, its secrets unfold, revealing tales once hidden in the code. Through dates and keys, we've learned to discern the art of encryption, a skill we yearn. So let us bid farewell, with knowledge in hand, ready to explore and understand. May our paths cross again in the realm of code, where mysteries unravel and stories are told. Until then, farewell, with a fond adieu, to new adventures awaiting me and you. In our previous tutorials, we delved into the essential looping constructs in Lua, the for loop and the while loop. We explored how the for loop is perfect for situations where we know exactly how many times we need to repeat a block of code. It's particularly useful for iterating over a range of values or elements in a table. We also covered the while loop, which is invaluable when we want to repeat a block of code as long as a certain condition remains true. This loop offers flexibility, allowing us to handle situations where the number of iterations is uncertain. Now in this tutorial, we're expanding our repertoire by introducing the repeat until loop. Unlike the while loop, the repeat until loop ensures that the loop body executes at least once before checking the loop condition. It's a powerful tool for scenarios where we want to guarantee the execution of a block of code before evaluating the loop condition. With this comprehensive understanding of looping constructs, we're well equipped to tackle a wide range of programming challenges in Lua. In this example, we initialize a counter variable with a value of 1. The repeat keyword starts the loop, and the loop body will execute at least once. Inside the loop body, we print the current value of the counter. After printing, we increment the counter by 1. The loop continues to execute until the condition counter 5 becomes true. Even if the condition is false initially, the loop executes at least once because the condition is checked at the end of the loop. We've explored 3 fundamental loop structures in Lua: the for loop, the while loop, and the repeat until loop. Each loop type serves a distinct purpose and offers unique advantages. The for loop is ideal when you know the exact number of iterations needed. It iterates over a specified range of values or a collection and executes the loop body for each iteration. It's concise and efficient for handling a predetermined number of loops. The while loop is used when you want to repeat a block of code as long as a specific condition remains true. It checks the condition before each iteration, making it suitable for scenarios where the number of iterations is not known in advance, but the condition for termination is clear. The repeat until loop ensures that the loop body executes at least once before checking the condition for termination. It's useful when you need to guarantee that a certain block of code runs at least once, regardless of the initial condition. It's particularly handy for situations where you want to execute a block of code until a specific condition becomes true. In summary, the for loop is best suited for a predetermined number of iterations, the while loop is used to repeat code until a condition becomes false, and the repeat until loop ensures that the loop body executes at least once before evaluating the termination condition. Understanding when to use each loop type empowers programmers to write more efficient and flexible code tailored to different scenarios and requirements. Welcome to our Lua programming tutorial. In this session, we'll dive into the power of repeat until loops. These loops are perfect for situations where you need to repeatedly execute a block of code until a certain condition is met. We'll explore how to use repeat until loops in conjunction with encryption techniques to create a robust message encryption and decryption system. Whether you're new to programming or looking to expand your knowledge, this tutorial will provide valuable insights into loop structures and their practical applications. Let's begin our journey into the world of repeat until loops. The script prompts the user to input a message to encrypt. Local key. This line declares a local variable named key without initializing it. The purpose of this variable is to store the user's input, which will be a number representing the encryption key. Repeat. This keyword marks the beginning of a repeat until loop, which is a type of loop that executes its block of code at least once and then repeats it until a specified condition is met. In this case, the loop continues until the user enters a valid input for the encryption key. Tonumber function converts the input, which is initially a string, into a numeric value. Until keyword marks the end of the repeat until loop and specifies the condition for its continuation. If key is not nil, it means the user entered a valid numeric value, and whether key falls within the specified range, 1 to 10. If the condition is true, the loop terminates, and the program continues execution, otherwise, the loop repeats, prompting the user to enter a valid input. Local encrypt initializes a local variable with an empty string. This variable will store the encrypted message as it is being generated. Local index with the value 1 will be used as an index to traverse through each character of the original message. Repeat marks the beginning of a new repeat until loop. This loop will continue executing until the condition is true. Local encode retrieves the ASCII value of the character at the index position in the original message. The string.byte function is used to convert the character to its ASCII value. The conditional statement checks if the variable encode contains a valid ASCII value, and it's not nil. If encode is valid, the code block inside the if statement will be executed. Here, the ASCII value of the character is incremented by the encryption key. This step is part of the encryption process, where each character's ASCII value is shifted by the specified key. String.char, in code, converts the modified ASCII value in code back to its corresponding character and appends it to the encrypted string. This builds the encrypted message character by character. Finally, the index variable is incremented by 1 to move to the next character in the original message. This ensures that each character is processed in the encryption loop. Overall, these lines of code are responsible for iterating through each character of the original message, encrypting it using a specified key, and building the encrypted message string. The process continues until all characters in the message have been encrypted. To ensure our encryption and decryption processes are functional and reversible, we need to design them in a way that allows us to undo the encryption operation to retrieve the original message. Here's how we can achieve that. Use symmetric encryption algorithms where the same key is used for both encryption and decryption. This means that the key used to encrypt the message must also be used to decrypt it. Ensure that the operations performed during encryption can be reversed during decryption. For example, if we use addition to encrypt the message, shifting ASCII values by a certain amount, we must use subtraction during decryption to revert the changes. Keep track of the encryption key used for each message. Without the correct key, decryption becomes impossible. It is crucial to securely manage and share keys only with authorized parties. Create a decryption algorithm that reverses the encryption process. This algorithm should take the encrypted message and the encryption key as input and output the original plaintext message. By following these principles, we ensure that our encryption process is reversible, allowing us to decrypt the messages and retrieve the original content. This reversibility is essential for the functionality and security of our encryption system. Once we have a complete script that includes both encryption and decryption functionality, we can separate the encryption and decryption codes. In this manner, we improve code maintainability, modularity, and reusability. It also makes it easier to understand and manage each component's functionality independently. Loops allow us to iterate over each character in a string, enabling us to examine, modify, or extract information from individual characters. The repeat until loop in Lua is particularly useful for string manipulation tasks where we need to repeat a block of code until a certain condition is met. For example, we can use a repeat until loop to validate user input until it satisfies certain criteria, such as ensuring the input falls within a specified range. Lua provides a variety of built-in string functions that enable us to perform common operations on strings, such as concatenation, substring extraction, character conversion, and pattern matching. By combining loops with string functions, we can create powerful algorithms for tasks like encryption, decryption, text parsing, searching, and pattern matching. For instance, we can use loops to iterate over each character in a string and apply encryption or decryption operations using string functions like string.byte and string.char. Loops allow us to efficiently process strings of arbitrary length, making it possible to handle large text data or perform complex string transformations without needing to manually manipulate each character. Overall, loops and string functions complement each other to provide a versatile toolkit for working with strings in Lua, enabling developers to perform a wide range of string manipulation tasks efficiently and effectively. Nested loops are loops within loops. They are used when you need to perform repetitive tasks that have multiple levels of iteration. Nested loops are often used when working with multidimensional data structures or when you need to iterate over combinations of elements. A nested loop is a loop inside another loop. This means that one loop is placed within the body of another loop. The inner loop will run its entire course for each iteration of the outer loop. In Lua, any loop construct can be used to create nested loops. This includes for, while, and repeat until loops. Here are examples of nested loops using each kind of loop construct, for, while, and repeat until, along with a mixed example. In our scenario, the inner loop j runs twice for each iteration of the outer loop I. So, the inner loop completes its entire cycle, from 1 to 2, 3 times because it's nested within the outer loop. A nested loop is not a distinct type of loop but rather a variation of loops where one loop is contained within another. It involves placing one loop inside another loop, allowing for more intricate and layered repetition in your code. This nesting creates a hierarchy of looping structures, enabling you to tackle more complex tasks by breaking them down into smaller, manageable steps. Here are some common scenarios where nested loops are used. When working with two-dimensional or multidimensional arrays, you may use nested loops to traverse each element in the grid. For operations involving matrices or grids, nested loops help access each element or perform calculations row by row or column by column. When dealing with nested data structures like nested lists or objects, nested loops help access or manipulate elements at different levels of nesting. In algorithms like searching or sorting, nested loops may be used to compare elements in a nested manner, such as in bubble sort or selection sort algorithms. They can be used to generate patterns or sequences that have multiple levels of repetition, such as printing shapes or creating fractals. In password cracking or generation algorithms, nested loops may be used to iterate over different combinations of characters or symbols. Nested loops provide a versatile approach to handle complex data structures and repetitive tasks that involve multiple levels of iteration. Many programming problems, especially those involving nested structures, require the use of nested loops to iterate through various levels of data and perform computations or checks. While nested loops can increase computational overhead, they are often the most efficient way to handle nested data structures and perform operations that depend on multiple levels of iteration. When used judiciously, nested loops can improve code clarity by encapsulating logic related to nested structures, making the code easier to understand and maintain. Understanding how to work with nested loops is a fundamental skill for programmers, as it teaches logical thinking and problem-solving strategies applicable to a wide range of scenarios. They provide a powerful mechanism for navigating through multidimensional data and executing tasks at different levels of granularity, making them an indispensable tool for any programmer. The x-coordinate typically represents the horizontal position in a two-dimensional space. It's often referred to as the width because it measures the distance from the left edge of the space to a specific point horizontally. In graphical applications, increasing the x-coordinate moves an object to the right, while decreasing it moves the object to the left. The y-coordinate represents the vertical position in a two-dimensional space. It's commonly referred to as the height because it measures the distance from the bottom edge of the space to a specific point vertically. In graphical applications, increasing the y-coordinate moves an object upward, while decreasing it moves the object downward. Together, the x and y coordinates define a point in a two-dimensional Cartesian coordinate system where the x-axis represents the horizontal dimension and the y-axis represents the vertical dimension. In programming, understanding and manipulating x and y coordinates is essential for tasks such as positioning objects on a screen, navigating game worlds, drawing shapes, and much more. We'll simulate coordinates using Lua variables target x, target y, current x, and current y. These variables represent points in a two-dimensional space, where target x and target y represent the target coordinates we want to find. Current x and current y represent the current coordinates being tested during our search. Here's what each variable signifies. Target x and target y, these variables define the coordinates of our target location. Target x represents the width from left to right, and target y represents the height from bottom to top. They specify the exact point we want to locate in our search. Current x and current y, these variables represent the current coordinates being tested in our search algorithm. We start our search from the initial coordinates, current x equals 12 and current y equals 7, and then iteratively move through the space to find the target coordinates. By simulating coordinates with these variables, we can demonstrate how to implement a search algorithm to find a specific point in a two-dimensional space, which is a fundamental concept in programming and game development. Local found coordinates. This line declares a local variable and initializes it to false. This variable will be used to track whether the target coordinates have been found. By default, when the search begins, we assume that the coordinates haven't been found yet. Repeat. This keyword starts a repeat until loop, which will continue executing until a certain condition is met. In this case, the loop will repeat indefinitely until the condition is explicitly checked within the loop body. Current x assigned to current x plus 1. This line increments the value of the current x variable by 1. It moves the search along the x-axis, effectively exploring the space from left to right. Current y assigned to 7. Sets the value of current y back to 7 after each iteration of the outer loop. This ensures that the search resets to the initial y coordinate for each new iteration along the x-axis. This allows us to traverse the space vertically, exploring different y coordinates while iterating over the x-axis. These lines collectively represent a nested loop structure, where the outer loop iterates over the x-axis, width, and the inner loop iterates over the y-axis, systematically exploring each point in the two-dimensional space until the target coordinates are found. The if statement checks if the current coordinates matches the target coordinates we are searching for. It compares the current vertical position with the desired vertical position and the current horizontal position with the desired horizontal position. If the current position matches the target coordinates, this line sets the variable found coordinates to true, indicating that the target coordinates have been found. The break keyword is used to exit the innermost loop immediately. In this context, when the target coordinates are found, we break out of the inner loop to stop further iterations. The end keyword closes the if block, indicating the end of the conditional statement. Until current y is greater or equal to target y. Until current x is greater or equal to target x. Or found coordinates. These lines control the loop's behavior, ensuring that it continues iterating until it meets one of the specified conditions, either the horizontal and vertical positions reach their respective target positions, or the target coordinates are found. If found coordinates then. checks the value of the variable found coordinates. If it evaluates to true, it means that the target coordinates have been found during the search process. Else, if found coordinates is not true, meaning the target coordinates were not found, the code inside the else block is executed. In summary, these lines control the output message based on whether the target coordinates were found or not. If found, it prints the coordinates, and if not found, it informs the user that nothing was found. We learned about the target x and target y variables, which represent the coordinates we want to find, and the current x and current y variables, which are used to iterate through the map. By incrementing current x and current y within nested loops, we systematically searched through the map to find the target coordinates. The found coordinates variable was used to track whether the coordinates were found during the search process. Finally, based on the value of found coordinates, we provided appropriate output messages to inform the user whether the target coordinates were found or not. In this tutorial, we explored the concept of using nested loops to search for specific coordinates within a simulated map. By understanding and applying nested loops in this context, you've gained valuable experience in using iterative techniques to solve specific problems in Lua programming. With this understanding, you're now equipped to apply nested loops in various programming scenarios to efficiently solve problems that require systematic iteration through data or structures. Keep practicing and exploring, and you'll continue to enhance your Lua programming skills. In this tutorial, we'll explore the concept of encryption using the string.byte function, but with a twist. Instead of using a fixed shift key for encryption, we'll randomize the shift key. This adds an extra layer of complexity and security to our encryption algorithm. Once we've encrypted our message using a random shift key, we'll then attempt to decrypt it. However, since we won't know the exact shift key used for encryption, we'll need to try all possible shift keys. This is where the nested loop comes into play. Local message hello world defines the message that we want to encrypt. Math.randomseed, os.time, sets the seed for the random number generator to the current time. This ensures that every time we run the program, the sequence of random numbers generated will be different. Local shift math random, 1 to 26. This line generates a random number between 1 and 26, inclusive. This random number will serve as the encryption key. By generating a random key within this range, we enhance the security of our encryption algorithm, as the shift amount is unpredictable without knowledge of the key. The variable encrypted message it is where we will store the encrypted version of the original message. Next line starts a loop that iterates over each character. Local encode within the loop retrieves the ASCII value of the current character. Encode plus shift applies the shift key to the ASCII value of the current character, effectively shifting it forward in the alphabet. String.char encode appends the encrypted character after applying the shift to the encrypted message string. At last, the print function it is used to show the result of the encryption process. By using a random shift key, the encryption becomes less predictable, making it harder for potential attackers to decrypt the message without knowing the exact key. This adds complexity and enhances the security of the encryption, as the encrypted message will vary each time it's encrypted with a different random key. Once we have confirmed that the encryption block works properly by encrypting the message with a random shift key, we can proceed to simulate a brute force attack to decrypt the message. In a brute force attack, we systematically try every possible combination of shift keys until we find the correct one that decrypts the message into a meaningful plaintext. This involves using nested loops to iterate through all possible shift key values and decrypting the message with each key until we find the one that produces a meaningful result. This process allows us to test the robustness of the encryption algorithm and evaluate its resistance against brute force attacks. In the line for I equals 1, 26 do. The loop is iterating from 1 to 26. This range represents all possible values for the shift key in a Caesar cipher, where each value corresponds to shifting the letters of the alphabet by a certain number of positions. Since there are 26 letters in the English alphabet, we iterate from 1 to 26 to cover all possible shift values. Each iteration of the loop represents a brute force attempt with a different shift key to decrypt the message. In the inner loop, we iterate over each character of the encrypted message to decrypt it. Within each iteration of the loop, we retrieve the ASCII value of the character at the current index j in the encrypted message using the string.byte function. This value represents the encoded character. After retrieving the ASCII value of the encoded character, we subtract the shift key I from it. This operation reverses the encryption process. During encryption, we added the shift value to each character's ASCII value, and now, during decryption, we subtract it to revert to the original ASCII value of the character. By subtracting the shift key I from the ASCII value of each character, we effectively decrypt the message, one character at a time. This process continues for each character in the encrypted message until the entire message is decrypted. When we subtract the shift key from the ASCII value of a character during decryption, the resulting value may fall below the ASCII value of lowercase a, which is 97, especially if the shift key was relatively large. For example, if the shift key is 25 and we are decrypting the character lowercase a, its ASCII value would be 97, and after subtracting 25, it would become 72, which is not within the range of lowercase letters. To handle this situation, we add 26 to the resulting value to wrap it back into the range of lowercase ASCII values. Adding 26 essentially wraps around the lowercase alphabet, ensuring that the decrypted character remains valid and consistent. We use string.char, decode, to convert the ASCII value stored in decode back into its corresponding character. By appending each decrypted character to decrypted message in each iteration of the inner loop, we reconstruct the original message. This tutorial demonstrated the power of nested loops in the context of encrypting and decrypting messages. By combining nested loops with string manipulation, we were able to simulate both encryption and decryption processes. First, we encrypted a message by randomly shifting the ASCII values of its characters. Then, we simulated a brute force attack by using nested loops to try all possible shift keys and decrypt the message. This process showcased how nested loops can be used to systematically explore and manipulate data in complex scenarios. Overall, this tutorial provided a hands-on example of how nested loops can be leveraged to solve real-world problems, such as encryption and decryption, and highlighted their importance in programming for tasks that require iterative and systematic approaches. In programming, loops are essential constructs used to execute a block of code repeatedly. Among various types of loops, an infinite loop is unique because it continues executing indefinitely until a specific condition is met or the program is terminated externally. In Lua, an infinite loop is typically implemented using a while loop with the condition true, which is always true, causing the loop to continue indefinitely. In this example, the loop prints executing repeatedly until the program is terminated manually. The break statement is used to exit the loop when a specific condition is met. It is indicated by the variable condition met in that case. In our last example, the loop waits for user input, and if the user enters Q, the loop breaks, terminating the program. Unlike other loops, infinite loops lack a predefined termination condition within the loop structure itself. Infinite loops require careful handling to avoid infinite execution, which can lead to system resource exhaustion or program freezes. Infinite loops are powerful constructs in programming, allowing code execution to continue indefinitely until explicitly terminated. Understanding how to create and control infinite loops is essential for effective program design and execution. Practice session task 1. Define the target password, numbers only. 2. Define a string containing all possible numbers from 0 to 9. 3. Initialize the attempts counter from 0. 4. Start an infinite loop to brute force the password. 5. Store in the infinite loop a variable with name brute_force. 6. Increment the attempts counter. 7. Generate a brute force attempt, random length between 3 and 6. 8. Append a random digit from the character's string to the brute force variable. 9. Check if the brute force attempt matches the target password. 10. Print the cracked password and exit the loop. 11. Print the attempt number and the current brute force attempt. Pause the video and take your time to solve the task, then come back to see my solution. Here is my solution. First line declares a local variable named target password and assigns it the value 1234, which is a string representing the target password. Next line declares a local variable named container and assigns it the string, which contains the digits from 0 to 9. Here we declare a local variable named attempts and initializes it with the value 0. Now we start a while loop that will continue indefinitely because the loop condition is always true. This line declares a local variable named brute force and initializes it as an empty string. Attempts is a variable that tracks the number of attempts made to crack the password. So, the line increases the value of attempts by 1 each time it is executed, effectively counting the attempts made to crack the password. These lines are used to determine the length of the brute force attempt, ensuring that it is a random length between 3 and 6 characters, and to randomly select characters from the container string for each position in the attempt. Here we append a randomly selected character from the container string to the brute force variable. The sub function extracts a single character at the index I from the container string and concatenates it to the existing brute force string. This process repeats for each character in the generated brute force attempt. Now we can check if the current brute force attempt matches the target password variable. If it is so, the condition evaluates to true, and further actions can be taken based on this condition. These lines are part of the loop structure and output control flow. Print is used to display that the password is found. Then breaks the loop immediately, as the password has been found. It exits the loop once the password is cracked. Else introduces the alternative block of code to be executed if the condition in the if statement is false. At last we print out the current attempt number and the corresponding brute force attempt. This print provides feedback on the progress of the brute force attack. The first end marks the end of the if-else block. The last end closes the loop structure. This task provided hands-on experience with using an infinite loop and string manipulation to simulate a common security attack scenario. We've covered a variety of loop structures, including for loops, while loops, repeat until loops, and the use of infinite and nested loops. We've explored how these loops can be used in different scenarios. There's one more loop structure to cover, the generic for loop. We'll save that for a future tutorial to ensure a solid understanding of the fundamentals. Math functions are essential components of programming, enabling us to perform various mathematical calculations efficiently within our code. In Lua, a wide range of math functions are available to handle diverse mathematical operations, from simple arithmetic to complex trigonometry and beyond. Math functions play a crucial role in programming for several reasons. They allow us to perform basic arithmetic operations such as addition, subtraction, multiplication, and division. These operations are fundamental to many programming tasks, including calculations, data manipulation, and algorithm implementation. Math functions like sine, cosine, and tangent are indispensable for dealing with angles and triangles. They find extensive use in applications like game development, graphics programming, physics simulations, and engineering. Functions for exponentiation and logarithmic operations are essential for tasks involving exponential growth, decay, and complex mathematical modeling. Lua provides functions for generating random numbers, which are vital for simulations, games, cryptography, and statistical analysis. Math functions facilitate data analysis by providing tools for statistical calculations, such as finding averages, standard deviations, and correlations. In this section, we'll explore miscellaneous math functions in Lua that cover various other mathematical operations. While these functions may not fall into specific categories, they offer additional capabilities for performing diverse calculations. Let's dive into our script to see some examples of these miscellaneous math functions in action. In this example, math.sqrt function calculates the square root of number, which is 16. The result is 4. The math.sqrt function is commonly used in mathematical calculations, physics simulations, and any application that requires square root calculations. It's particularly useful in scenarios involving geometry, physics, and engineering, where knowing the length of a side or the magnitude of a vector is crucial. In summary, math.sqrt is a fundamental math function in Lua that computes the square root of a given number, making it indispensable for a wide range of mathematical and scientific computations. The math.max function is used to determine the maximum value among a set of numbers. In this example, math.max function compares the numbers 10, 5, 20, and 15, and determines that 20 is the maximum value. The math.max function is commonly used in scenarios where you need to find the largest value among a group of numbers. It's useful in various applications, such as finding the highest score in a game, determining the maximum temperature in weather data, or identifying the largest quantity in a dataset. In summary, math.max is a versatile math function in Lua that efficiently identifies the maximum value from a given set of numbers, making it essential for comparisons and decision-making in programming. The math.min function is the counterpart of math.max. It is used to determine the minimum value among a set of numbers. In this example, math.min compares the numbers 10, 5, 20, and 15, and determines that 5 is the minimum value. The math.min function is commonly used in scenarios where you need to find the smallest value among a group of numbers. It's useful in various applications, such as determining the lowest price in a list of products, identifying the earliest date in a dataset, or finding the minimum distance between 2 points. In summary, math.min is a fundamental math function in Lua that efficiently identifies the minimum value from a given set of numbers, making it essential for comparisons and decision-making in programming. We are already familiar with math.random and randomseed, so let's recap. Seeding the random number generator ensures that the sequence of random numbers is different each time the program is run. Using math.random with specified bounds allows you to generate random numbers within a specific range. Random numbers are commonly used in various applications, such as generating random values for simulations, games, cryptographic functions, and more. In summary, this code snippet demonstrates how to generate random numbers in Lua, a fundamental feature often used in programming for randomness and unpredictability. In this tutorial, we'll create a simple script to simulate a character's health in a game. We'll explore how to handle damage and automatic healing using potions. Throughout the tutorial, we'll use fundamental math functions like math.max and math.min to control the character's health, providing an engaging example of practical usage. In these lines, we are setting up the initial parameters for a character's health management system in a game. Max health establishes the maximum health value the character can have, serving as a reference point for their overall well-being. Current health initializes the character's current health to be equal to the maximum health, effectively starting the game with full health. Auto potion defines a threshold for the character's health. If their health falls below this threshold, 30% in this case, the game automatically triggers the use of a healing potion to help them recover. Potion amount determines the effectiveness of the healing potion. In this case, the potion restores the character's health to its maximum value, providing a full recovery. These lines establish the foundation for managing the character's health and ensuring they can maintain their well-being throughout the game by automatically using healing potions when necessary. While true do initiates an infinite loop, representing the ongoing gameplay loop. This line simulates the character taking damage. The math.random function generates a random number between 5 and 15, indicating the amount of damage inflicted on the character's health. This value is subtracted from the current health. Next line ensures that the character's health doesn't go below 0. If the calculated health after taking damage is negative, it's set to 0 to prevent negative health values. print function. It is used to show the health of the character to the console, allowing the player to see how much health they have after taking damage. If the current health is less than the auto potion, then this conditional statement checks if the character's health is below the threshold set by auto potion. If the health falls below this threshold, it triggers the activation of a healing potion. Next line prints a message to notify the player that their health is below the designated threshold. It prompts them to take action by using a healing potion. Math min current health plus potion amount, max health. This line represents the application of the healing potion. It adds the potion amount to the character's current health, but ensures that the health doesn't exceed the maximum health limit, max health. This prevents the character from having more health than their maximum capacity. The print function informs the player that a healing potion has been used and displays the character's updated health status after using the potion. The os execute function is used to execute shell commands, and in this case, the command being executed is sleep1, which instructs the operating system to suspend the execution of the script for 1 second. This is often used to introduce delays in scripts, such as creating a pause between iterations of a loop. It's a powerful tool that enables interaction with the underlying operating system. With os execute, you can run almost any shell command that you could run directly from the command line. While this function provides a way to interact with the operating system, it's important to note that its behavior might vary depending on the platform. For example, a command that works on Linux might not work the same way on Windows. Using os execute can introduce security risks if the commands being executed are based on user input and not properly sanitized. It's important to validate and sanitize any inputs used with os.execute to prevent command injection vulnerabilities. By default, os execute blocks the Lua script until the command completes execution. However, you can run commands asynchronously by using operating system-specific mechanisms or by running them in background threads. The function returns true if the command was executed successfully, and nil otherwise. Additionally, you can capture the exit status of the command using the status parameter. Overall, os.execute provides a way to extend the capabilities of Lua scripts by allowing interaction with the underlying operating system, but it should be used judiciously and with caution, especially when dealing with user input or sensitive operations. Instead of generating a random number within a specific range, for the inflicted damage, we could use math.sqrt function with max health variable to determine the damage inflicted on the character. This change would cause the damage to be proportional to the square root of the character's maximum health. By understanding these fundamental concepts and functions, you can create more complex game mechanics and simulations in Lua. Exponential and logarithmic functions are fundamental concepts in mathematics and are extensively used in various fields such as science, engineering, finance, and computer science. Let's delve into an introduction to these functions. An exponential function is a mathematical function of the form where a and b are constants, with b being the base of the exponential function. X is the exponent. Exponential functions have the unique property that the rate of change of the function with respect to the independent variable x is proportional to the value of the function itself. This property leads to exponential growth or decay, depending on whether the base b is greater than 1 meaning growth or between 0 and 1 meaning decay. Exponential functions exhibit rapid growth or decay and are characterized by a base raised to a variable exponent. Applications of the exponential functions include model population growth, compound interest, radioactive decay, and other phenomena where the rate of change is proportional to the current value. A logarithmic function is the inverse of an exponential function. It is written in the form where b is the base of the logarithm, x is the argument of the logarithm. Logarithmic functions are used to solve exponential equations and to convert exponential equations into linear equations, making them easier to analyze and manipulate. Logarithmic functions are used in signal processing, data compression, pH scale in chemistry, and solving exponential equations. Local variable x assigned to the value 2. Here, x represents the exponent in the exponential function. The second line calculates the value of e raised to the power of x using the math.exp function. The function returns the exponential value of its argument, x in this case. The last line prints the result using string format to format the output. %d is a placeholder for the exponent x, and %f is a placeholder for the exponential result. N.2f specifies that the floating point number should be formatted to display 2 decimal places. The value of x and exp result are passed to string format as additional arguments. Overall, this code calculates and prints the value of e raised to the power of 2, demonstrating the usage of the math.exp function in Lua. The first line declares a local variable number and assigns it the value 10. This represents the number for which we want to calculate the natural logarithm. The second line calculates the natural logarithm of the number using the math.log function. The function returns the natural logarithm of its argument, number in this case. So, log result will contain the natural logarithm of 10. The last line prints the result using string format to format the output. %d is a placeholder for the number, and %f is a placeholder for the natural logarithm result. .2f specifies that the floating point number should be formatted to display 2 decimal places. The value of number and log result are passed to string format as additional arguments. Overall, this code calculates and prints the natural logarithm of 10, demonstrating the usage of the mathlog function in Lua. Mathlog10 is a built-in mathematical function in Lua that calculates the base 10 logarithm of a number. This function is available in Lua starting from version 5.3. Note: mathlog calculates the natural logarithm base e of a number x. Mathlog10 calculates the base 10 logarithm of a number x. So, the main difference between the two functions lies in the base of the logarithm they compute. Mathlog computes natural logarithms base e, while mathlog10 computes logarithms to the base 10. Example: mathlog with argument 100 returns approximately 4.60517. As it computes the natural logarithm of 100. Mathlog10 with argument 100 returns exactly 2. As it computes the base 10 logarithm of 100. Understanding the differences between mathlog and mathlog10 allows you to choose the appropriate function based on the base of the logarithm you need for your calculations. If you are using an older version of Lua that does not have the mathlog10 function, you'll need to simulate its behavior by using a workaround. Here's how you can achieve this. We define a custom function log10 that calculates the base 10 logarithm of x by dividing the natural logarithm of x by the natural logarithm of 10. This custom function replicates the behavior of mathlog10 for older Lua versions where this function is not available. By using this approach, you can achieve the same result as mathlog10 even in older versions of Lua. It's a common practice to create custom functions to emulate the behavior of missing or newer built-in functions in older versions of programming languages. Understanding these mathematical functions is essential for various programming tasks, especially in areas like scientific computing, data analysis, and game development. In wrapping up this tutorial, remember that mathematical functions are powerful tools in programming, enabling you to perform a wide range of calculations efficiently. By mastering these functions, you're equipped to tackle complex problems in Lua programming. In this tutorial, we will explore the powerful math.exp function and its application in financial calculations. Through practical examples, we'll learn how to compute compound interest and monthly loan payments with ease. Let's dive in and unlock the potential of exponential functions in Lua programming. This code segment prompts the user to input the loan amount and reads the input from the console. It then converts the input string into a numeric value using tonumber function, allowing for mathematical operations later in the program. In the next code segment, the program prompts the user to input the duration to repay the loan, measured in years. The entered value is then converted from a string to a numeric format using again the tonumber function for further processing. Now the user is prompted to input the interest rate for the loan, expressed as a percentage. The entered value is then captured as a string using the io_read function. Subsequently, the string input is converted into a numeric value using the tonumber function and stored in the variable rate percentage. Here rate percentage is converted from a percentage format to a decimal format. This conversion is achieved by dividing the rate percentage by 100, resulting in a decimal representation of the interest rate, which is then stored in the variable rate. In the subsequent code block, the compound interest on the loan is calculated using the formula for continuously compounded interest. The math.exp function raises Euler's number, e, to the power of the product of the interest rate and the duration to repay the loan in years. This exponential calculation represents the growth of the loan amount over time due to compounded interest. The resulting compound interest value is stored in the variable compound interest, and then printed to the console with an appropriate message. Next, we will convert the annual interest rate to a monthly rate for further calculations. This line calculates the monthly interest rate by dividing the annual interest rate by 12 to convert to monthly, and then by 100 to convert from percentage to decimal. Here we will compute the total number of months by multiplying the duration to repay the loan in years by 12, converting it from years to months. This formula calculates the monthly payment amount for an amortizing loan. It takes into account the loan amount, the monthly interest rate, and the total number of months over which the loan is repaid. By considering these factors, the formula determines the fixed monthly payment required to pay off the loan within the specified time frame. The resulting monthly payment is then printed to the console with an appropriate message. This tutorial has demonstrated the process of calculating compound interest and monthly loan payments using Lua programming. By leveraging the math.exp function for exponentiation, we were able to accurately compute compound interest based on user input for loan amount, duration, and interest rate. Additionally, we utilized mathematical formulas to convert annual interest rates to monthly rates and determine fixed monthly payments for amortizing loans. The importance of math.exp function cannot be overstated, as it allows us to handle complex exponential calculations with ease, particularly in financial contexts such as compound interest calculations. Mastering this function opens up a wide range of possibilities for implementing advanced mathematical operations in Lua programming, making it an invaluable tool for developers working with financial applications or any domain requiring exponential calculations. Welcome to our short and concise tutorial on simulating a simple machine learning model in Lua. In this tutorial, we'll explore how to create a basic machine learning simulation using Lua, keeping the code clear and consistent for easy understanding. By the end, you'll have a grasp of how to implement a simple machine learning concept in Lua, presented in a visually appealing and concise format. These lines initialize the start and stop variables to define the range of numbers for our simulation, from 1 to 10, and print a message indicating the start of the simulation. Next we set up nested loops. The outer loop iterates through numbers in the defined range, from start to stop, while the inner loop prints 5 dots to simulate a process happening for each iteration of the outer loop. The IO_flush function is used to ensure that any pending output is immediately written to the output stream. This function is particularly useful when we want to ensure that data is written to the output immediately without waiting for buffering. In our simulation, we use IO_flush after printing dots to ensure that the dots are immediately displayed on the screen, providing a more interactive and real-time experience for the viewer. IO_flush function is used to forcibly write any pending data in the output buffer to the underlying output stream. In Lua, output to the console or a file is often buffered, meaning that data is stored in memory temporarily before being written to the output device. This buffering can improve performance by reducing the number of write operations, but there are situations where immediate output is desired, such as when displaying progress indicators or interactive messages. By calling IO_flush, you ensure that any buffered output is immediately written to the output device, making it visible to the user or available for further processing. This function is commonly used in situations where real-time or interactive output is required, such as in command line interfaces, progress bars, or simulations. os_execute, sleep 0.1, uses the os_execute function in Lua to execute a shell command, specifically the sleep command, which pauses the execution of the script for a specified amount of time. In this case, sleep 0.1 pauses the script for 0.1 seconds, simulating a short delay or process happening in real time. This can be useful for creating animations, simulating real-time processes, or adding delays between actions in a script. It is important to sanitize any input passed to the os_execute function to prevent security vulnerabilities, such as command injection attacks. In this case, since we are using a hard-coded string, there is no user input involved, so the risk is minimal. However, it is still a good practice to sanitize or validate any input if it comes from an untrusted source or could be modified by external factors in a production environment. Local log value assigned to math log I. This line calculates the natural logarithm of the variable I using the math log function in Lua. The result is stored in the variable log value. Local prediction assigned to log value greater than 2 and yes or no. This line assigns a value to the variable prediction based on whether the log value is greater than 2. If log value is greater than 2, it assigns the string yes to prediction. Otherwise, it assigns the string no. This is a concise way of writing a conditional expression in Lua, known as a ternary operator. Local result string assigned to string format. The line uses the string format function and substitutes placeholders in the format string with corresponding values provided as arguments. The placeholders specify the format for each value. %d for an integer. At that case I. %.2f for a floating point number with 2 decimal places. At that case log value variable. And %s for a string. At that case the prediction variable. Note: in a real scenario, the line using the string format function should be written on a single line. However, for the sake of visibility and clarity in this tutorial, we have split the line into 2 separate lines. This allows us to explain each part of the format string and its corresponding values more clearly. When writing code in practice, it's common to keep such lines concise and readable by fitting them on a single line whenever it is possible. Finally, the print function is used to display the output of the script. In conclusion, we have successfully simulated a simple machine learning model in Lua. Throughout the tutorial, we learned how to initialize variables to define the range of data points for our simulation, use nested loops to simulate processes and generate data points, calculate the natural logarithm of each data point using the math.log function, make predictions based on a simple decision rule, format and print the results using the string format function. By following these steps, we've gained a basic understanding of how to implement a simple machine learning concept, presented in a clear and concise format. In this tutorial, you'll learn how to create a script that evaluates the strength of passwords based on their composition and length. You'll see how to categorize passwords as weak, normal, or strong, providing valuable insights into their security levels. Let's dive in and empower your coding skills to enhance password security. The script prompts the user to input a password and reads it from the standard input. In Lua, IOREAD *L is used to read a line of text from the standard input, which typically represents the keyboard input. The *L parameter specifies that it should read until the end of the line. This means that the user can input a sequence of characters until they press the Enter key, and Lua will capture that entire line as the input. This method is commonly used for reading user input that spans across multiple words or characters until the Enter key is pressed, making it suitable for capturing entire lines of text from the user. This block of code checks if the entered password meets the criteria of containing only letters and numbers. If the password is empty, nil, or contains any characters other than letters and numbers, it prompts the user to enter a valid password and terminates the script. The string on the first line is a pattern used in Lua's pattern matching system. Here's what it means. Caret anchors the pattern to the beginning of the string. %w matches any alphanumeric character, letters and numbers. Plus matches one or more occurrences of the preceding pattern. $ anchors the pattern to the end of the string. Overall, this pattern ensures that the entire string consists of one or more alphanumeric characters, with no other characters allowed before or after. This pattern is commonly used in Lua programming. It can be used for various input validation tasks where you want to ensure that the input contains only alphanumeric characters. Some other potential uses include username, file name, and URL validations. Also input sanitization. And these are just a few examples, but the pattern can be adapted to various scenarios where such validation is required. The length of the password is used in further calculations to determine the total number of possible combinations of characters, which is crucial for evaluating the password's strength and security level. The variable character set represents the total number of possible characters that can be used in the password. It includes upper and lowercase letters meaning 26 plus 26 is equal to 52, and numbers from 0 to 9 meaning 10. Therefore, the total number of characters is 52 for letters, plus 10 for numbers. The total is 62 characters. This line calculates the total number of possible combinations of characters for the password based on the length of the password and the size of the character set. It raises the size of the character set to the power of the password length. This calculation represents the total number of unique combinations possible for the password. This next line calculates the strength of the password in terms of its entropy or unpredictability. It uses the logarithm function to compute the logarithm of the total number of combinations to the base 10. In simple terms, it determines how many bits of entropy the password possesses. Entropy measures the uncertainty or randomness of a password. A higher entropy value indicates a more unpredictable password, making it harder to guess or crack. Note: if you are using Lua version 5.3 or higher, then you can indeed simplify the calculation of strength by using math.log10 function directly. These lines set thresholds to categorize the strength of the password into different security levels. Local weak threshold assigned to 20. This line defines a threshold value of 20. Any password with a strength below this value will be categorized as weak. Local strong threshold assigned to 40. This line defines a threshold value of 40. Any password with a strength equal to or greater than this value will be categorized as strong. These thresholds help in determining the security level of the password based on its calculated strength. Depending on where the strength value falls between these thresholds, the password will be categorized as weak, normal, or strong, providing a clear indication of its security level. Local strength category declares a variable to store the category of the password strength. If the strength is less than the weak threshold, it assigns the category weak to strength category. If not, it proceeds to the Elseif statement. The Elseif statement checks if the strength value is strictly less than the strong threshold. If the strength is less than the strong threshold, but not less than the weak threshold, it assigns the category normal to strength category. If not, it proceeds to the else block. The else block is executed only if the strength value is strictly greater than the strong threshold. In this case, it assigns the category strong to strength category. This block of code effectively categorizes the password strength into weak, normal, or strong based on the calculated strength value and the predefined thresholds, providing a clear indication of its security level. This line prints the estimated number of bits of entropy for the password. It concatenates the string estimated numbers of bits of entropy with the value of the variable strength, which represents the strength of the password in terms of bits of entropy, and prints the result. The last line prints the password security level based on the categorized strength. It concatenates the string password security level with the value of the variable strength category, which represents the security level of the password, and prints the result. The print functions provide additional information to the user about the strength and security level of the password, helping them understand the assessment made by the script. In this tutorial, we've explored how to create a Lua script to assess the strength of passwords. By analyzing the composition and length of passwords, we categorize them into weak, normal, or strong security levels, providing valuable insights into their vulnerability to brute force attacks. Through this tutorial, you've gained the knowledge to enhance password security in your applications, ultimately contributing to better protection of sensitive information. Keep practicing and exploring further to strengthen your skills in Lua programming and cybersecurity. Rounding and absolute value functions are fundamental tools in mathematics and programming, often used to manipulate and manage numerical data. These functions play crucial roles in various applications, from financial calculations to data analysis. The absolute value function returns the distance of a number x from 0 on the number line, regardless of its sign. In programming languages such as Lua, the math.abs function is used to compute the absolute value of a number. For example, math.abs -5 returns 5, as the absolute value of -5 is 5. Rounding functions are used to approximate a number to a nearby integer or specified decimal place. Two common rounding functions are mathCeil and mathFloor. MathCeil with argument x rounds x up to the nearest integer. MathFloor with argument x rounds x down to the nearest integer. Additionally, custom rounding functions, such as mathRound, can be defined to round a number to the nearest integer. These custom functions typically utilize mathFloor or mathCeil along with a specific rounding logic. Understanding and mastering these rounding and absolute value functions is essential for accurate numerical computations and data manipulation tasks in programming. An absolute value represents the distance of a number from 0 on the number line, regardless of its sign. So, for positive numbers, the absolute value remains the same, but for negative numbers, it becomes positive. In the provided example, the absolute value of x, it is the same because 4.5 is already positive. The absolute value of y remains also the same because 5.8 it is also positive. However, the absolute value of z becomes positive because minus 4.5 is negative and its absolute value is 4.5. So, even though the values of x and z are different, their absolute values turn out to be the same because absolute value measures distance from 0, not the direction. Let us dive deeper into the next example and discuss why we get the results we do, as well as the differences between them. The math.ceil function in Lua rounds a given number up to the nearest integer, which could be positive or negative, depending on the input value. It does not strictly go to positive, rather, it rounds towards positive infinity when dealing with negative numbers. First, let us break down our code. Variable x equals 4.5. The math.ceil function rounds x up to the smallest integer greater than or equal to 4.5. The result is 5, because 5 is the smallest integer greater than 4.5. Variable y equals 5.8. Again, math.ceil rounds y up to the smallest integer greater than or equal to 5.8. The result is 6, because 6 is the smallest integer greater than 5.8. Variable z equals negative 4.5. Here math.ceil rounds c up to the smallest integer greater than or equal to negative 4.5. This might seem a bit tricky, but it's important to remember that math.ceil rounds towards positive infinity. So, the result is negative 4, because it is the smallest integer greater than negative 4.5. Understanding the behavior of math.ceil function is essential for tasks like rounding up prices, calculating quantities, or any situation where you need to ensure values are rounded up to the nearest integer. Variable x equals 4.5. The math.floor function returns the largest integer less than or equal to 4.5. The result is 4, because 4 is the largest integer that is less than or equal to 4.5. Variable y equals 5.8. Again, math.floor returns the largest integer less than or equal to 5.8. The result is 5, because 5 is the largest integer that is less than or equal to 5.8. Variable z equals negative 4.5. For negative numbers, math.floor still returns the largest integer less than or equal to the given number. Since z is negative, the result is negative 5, because it is the largest integer that is less than or equal to negative 4.5. The math.floor function rounds a number down to the nearest integer. It always returns a value less than or equal to the input number. When dealing with negative numbers, math.floor returns the next lower integer. Math.floor rounds down, while math.ceil rounds up. Math.floor moves towards negative infinity for negative numbers, while math.ceil moves towards positive infinity. Their behavior is opposite when it comes to handling decimal values. Math.floor removes the decimal part to go down, while math.ceil increments the integer to go up. Understanding these opposite characteristics helps in choosing the appropriate rounding method based on the specific requirements of your program. Welcome to our tutorial showcasing the remarkable capabilities of math.ceil and math.floor functions in managing financial data impacted by inflation. In this tutorial, we will delve into how these functions enable precise rounding of inflation-adjusted values, revealing the intricate dynamics of monetary depreciation over time. By the end, you will appreciate the significance of accurate rounding in financial analysis and planning. The first line defines a variable named annual payment, representing the payment or income received per year. In this case, it is set to $15,000, indicating an annual payment amount. The next line defines another variable named annual inflation, representing the inflation rate for the entire year. It is expressed as a percentage, 5.9%, indicating the expected increase in prices or decrease in the purchasing power of money over the course of a year. This line of code calculates the inflation rate per month based on the annual inflation rate. The annual inflation rate is divided by 12 to get the monthly inflation rate. This division accounts for the fact that there are 12 months in a year. Then, dividing by 100 converts the percentage value to a decimal. So, for example, if the annual inflation rate is 5.9%, this line calculates the monthly inflation rate as 5.9 divided by 12 divided by 100, which is approximately 0.49%. This represents the expected increase in prices or decrease in purchasing power for each month due to inflation. Next, our code calculates the decrease in the value of money per month. Multiplying the annual payment by the monthly inflation rate calculates the amount by which the value of the money decreases each month. For example, if the annual payment is $15,000 and the monthly inflation rate is 0.49, means that the value of the money decreases by approximately $73.50 each month due to inflation. Here the code calculates the decrease in the value of money over the course of a year. Multiplying the monthly decrease by 12 calculates the total decrease in the value of money over the span of a year. Since there are 12 months in a year, this multiplication accounts for the cumulative effect of inflation over each month. For example, if the monthly decrease is $73.50, then 73.50 multiplied by 12 means that the value of the money decreases by approximately $882 over the course of a year due to inflation. This piece of code is designed to round up the calculated decrease in the value of money per month and per year to 2 decimal places. The math.seal function is utilized to round up the value of the monthly decrease multiplied by 100 to the nearest integer. By first multiplying by 100, the decimal point is shifted 2 places to the right, enabling the seal function to round to the nearest hundredth. Then, dividing by 100 restores the decimal point to its original position, effectively rounding up the result to 2 decimal places. This rounded up value is stored in the variable monthly roundup. Similarly, the next line applies the same rounding process to the value of the annual decrease multiplied by 100, ensuring rounding up to the nearest integer using math.seal. Again, the multiplication by 100 and subsequent division by 100 ensure rounding to 2 decimal places. The resulting rounded-up value is stored in the variable annual roundup. In summary, these lines ensure that the calculated decrease in the value of money per month and per year is rounded up to 2 decimal places, providing more accurate and precise results for analysis and presentation. Here, by directly multiplying monthly inflation by 100, the code accurately calculates the monthly inflation rate as a percentage. However, this approach retains the decimal precision of the original value, which may result in a percentage with more decimal places than typically presented. Given the sensitivity of financial calculations to even small changes in percentages, maintaining this precision could be important for accuracy, especially in contexts where the exact percentage value is critical for further analysis or decision-making. Therefore, the code represents the monthly inflation rate without rounding to 2 decimal places, prioritizing accuracy and precision in the calculation over presentation aesthetics. Our next lines provide a clear presentation of the calculated decreases in the value of money per month and per year, ensuring that the values are rounded up for better clarity and accuracy in financial analysis. Next lines of code round down the calculated decrease in the value of money per month and per year to 2 decimal places. Rounding both up and down allows for a more comprehensive analysis, enabling comparison between the rounded up and rounded down values to determine which rounding method is more appropriate or convenient for a given scenario. By providing both rounded up and rounded down values, the code facilitates a comparison of the potential impact of inflation on financial calculations from both a more optimistic and a more conservative perspective. This comparison can help decision-makers choose the rounding method that aligns best with their goals, risk tolerance, and overall strategy. Therefore, rounding both up and down provides valuable insights into the potential range of outcomes, empowering users to make more informed decisions based on their specific needs and preferences. This tutorial demonstrates how MathSeal and MathFloor can be used to round values to achieve different levels of precision. The precision is crucial in financial calculations where small differences can have significant impacts. These functions provide versatile rounding options. MathSeal rounds up to the nearest integer, while MathFloor rounds down. This versatility allows for fine-tuning calculations to meet specific requirements. By rounding values both up and down, enables a comparative analysis, allowing users to assess the potential impact of rounding on financial outcomes. This comparison empowers decision makers to choose the most suitable rounding method based on their objectives and risk tolerance. By providing insights into the consequences of rounding choices, users are better equipped to make decisions aligned with their goals and strategies. Overall, the tutorial serves as an educational resource, showcasing the practical application of MathSeal and MathFloor in financial modeling. It highlights their power in managing and presenting financial data accurately and effectively. In this tutorial, we will introduce you to a few of the trigonometric functions available in Lua's math library. Firstly, we are setting a variable x to store the value of pi divided by 4, where pi represents the mathematical constant pi, approximately equal to 3.14. The value pi divided by 4 represents an angle of 45 degrees in radians. This sets the stage for using the variable x to demonstrate various trigonometric functions like sine, cosine and tangent at that case, which we will cover in the subsequent part of the tutorial. In Lua, math pi is not a function but a constant value representing the mathematical constant pi. It behaves like a predefined value that remains constant throughout the program execution and cannot be changed. You can directly access math pi to obtain the value of pi in your calculations without needing to define it yourself. It's a useful tool for mathematical computations involving angles, circles, and other geometric calculations. We will now use the sine function with the argument x, where x holds the value of pi divided by 4 radians. The sine function calculates the ratio of the length of the side opposite the angle to the length of the hypotenuse in a right triangle. When we apply the sine function to the angle represented by pi divided by 4, it calculates the ratio of the length of the side opposite that angle to the length of the hypotenuse in a right triangle. This ratio represents the sine of the angle pi divided by 4. We will now use the cosine function with the argument x, where x holds once again the value of pi divided by 4 radians, just like before with the sine function. The cosine function calculates the ratio of the length of the side adjacent to the angle to the length of the hypotenuse in a right triangle. When we apply the cosine function to the angle represented by pi divided by 4, it calculates the ratio of the length of the side adjacent to that angle to the length of the hypotenuse in a right triangle. This ratio represents the cosine of the angle pi divided by 4. Note: in our example with pi divided by 4 radians or 45 degrees, its complement is also pi divided by 4 radians. Therefore, when we calculate the sine and cosine of pi divided by 4 radians, we will get the same result due to their complementary relationship. We will now use the tangent function with the argument x, where x holds the value of pi divided by 4 radians, just like before with the sine and cosine functions. The tangent function calculates the ratio of the length of the side opposite the angle to the length of the side adjacent to the angle in a right triangle. When we apply the tangent function to the angle represented by pi divided by 4, it calculates the ratio of the length of the side opposite the angle pi divided by 4 to the length of the side adjacent to the angle pi divided by 4 in a right triangle. This ratio is equivalent to dividing the sine by the cosine of the angle. Since the sine and cosine of pi divided by 4 radians are equal, when we divide sine by cosine, the result is 1. Therefore, the tangent of pi divided by 4 radians is 1. Understanding the trigonometric functions sine, cosine, and tangent provides a powerful toolkit for solving various mathematical problems involving angles and triangles. By exploring their relationships and applications, we have gained insight into how these functions work and their significance in mathematics and beyond. Keep practicing and exploring to deepen your understanding of trigonometry and its applications. While we have covered some of the most commonly used math functions until now, Lua's math library offers a wide range of mathematical functions beyond what we have learned. Once you feel comfortable with Lua, you can explore and learn about these additional math functions. They can be incredibly useful for various mathematical computations and programming tasks. Experimenting with different functions will deepen your understanding of Lua and enhance your problem-solving skills. In our tutorials thus far, we have delved into the realm of Lua programming, exploring its capabilities and syntax. Throughout our journey, we have primarily focused on utilizing built-in functions provided by Lua. These functions are integral components of Lua's standard library, meticulously crafted to simplify, expedite, and streamline the coding process. Built-in functions serve as the cornerstone of Lua programming, imbuing developers with a rich arsenal of tools to tackle diverse challenges. They encapsulate a plethora of functionalities, spanning from mundane tasks like printing text to complex mathematical computations. By harnessing these predefined functions, programmers can circumvent the arduous task of reinventing the wheel, fostering code efficiency and maintainability. Furthermore, the integration of built-in functions into Lua's core library underscores the language's versatility and adaptability to myriad use cases, ranging from scripting to game development. Built-in functions are seamlessly integrated into Lua's standard library, constituting an extensive repertoire of utilities readily accessible to developers. This comprehensive library encompasses a myriad of domains, encompassing string manipulation, mathematical operations, file handling, and more. By leveraging Lua's rich ecosystem of built-in functions, developers can orchestrate intricate workflows with finesse, obviating the need for external dependencies or cumbersome workarounds. Thus, Lua's expansive library of built-in functions stands as a testament to the language's robustness and versatility. At the core of built-in functions lies a fundamental principle: to simplify and expedite the coding process. By providing prepackaged solutions to common programming tasks, built-in functions empower developers to write concise, elegant code without sacrificing efficiency or performance. Moreover, their integration into Lua's standard library fosters code reusability, enabling developers to leverage existing solutions to expedite development cycles. Consequently, built-in functions serve as catalysts for innovation, enabling developers to focus on crafting high-level logic rather than grappling with low-level implementation details. While built-in functions in Lua provide a robust foundation for programming tasks, there inevitably comes a point where their capabilities may not suffice for specific requirements. This is where the concept of custom functions comes into play. Custom functions, also known as user-defined functions, afford developers the flexibility to encapsulate reusable blocks of code tailored to their unique needs. Despite the vast array of functionalities offered by Lua's standard library, the diversity of programming challenges necessitates the creation of custom functions to address specific use cases effectively. In essence, while built-in functions serve as indispensable tools in Lua programming, the evolution of software development invariably necessitates the creation of custom functions. These functions, imbued with domain-specific logic and tailored to project-specific requirements, play a pivotal role in realizing the full potential of Lua programming. As we embark on the journey of custom function creation, let us embrace the opportunity to unleash our creativity, innovation, and problem-solving prowess in the pursuit of elegant, efficient solutions. In programming, a function is a block of organized, reusable code that performs a specific task. Functions provide a way to modularize code, making it more manageable, readable, and maintainable. The function keyword is used to define a function in most programming languages. It signifies the beginning of a function declaration. A function typically has a name that identifies it uniquely within the program. Following the function name, there are parentheses that may contain parameters. Parameters are variables that represent values passed to the function when it is called. If a function does not have a name, it is called an anonymous function. Anonymous functions are commonly used in languages that support higher-order functions, allowing functions to be passed as arguments to other functions or assigned to variables. Parameters are variables listed inside the parentheses of a function declaration. They act as placeholders for values that will be passed to the function when it is called. Parameters allow functions to operate on different data each time they are called, enhancing their flexibility and reusability. The body of a function contains the code that defines the function's behavior. The function body contains the instructions or statements that execute when the function is called. The return statement is used to specify the value that a function should return to the caller. It typically appears inside the function body and is followed by the value to be returned. Lua allows functions to return multiple values simultaneously, but you have the flexibility to capture as many or as few of those values as necessary when calling the function. In Lua, the return statement marks the end of a function's execution, and no code or statements can be added after it within the same block of code. Additionally, no code or statements can be added after the end keyword that marks the end of the function definition. Functions encapsulate code by grouping related instructions together. This encapsulation promotes code organization, reusability, and maintainability by allowing developers to break down complex tasks into smaller, more manageable units. By understanding these fundamental components of functions, programmers can effectively leverage functions to structure their code and create more robust and scalable software solutions. In conclusion, functions are fundamental building blocks in programming, enabling modularity, reusability, abstraction, scalability, readability, maintainability, code organization, and facilitating testing and debugging. While built-in functions provided by the language's standard library offer essential functionalities and expedite common tasks, custom functions empower developers to address specific requirements and tailor solutions to their unique needs. By leveraging both built-in and custom functions judiciously, programmers can create well-structured, maintainable, and scalable software systems that efficiently tackle diverse challenges. In this Lua code snippet, we delve into the intricacies of variable scope and error handling. Let us embark on a journey to understand how Lua manages variables and gracefully handles errors, unveiling the nuances that shape robust Lua programming practices. This code demonstrates variable scope in Lua. It declares a global variable, defines a function with a local variable, and prints both variables' values inside the function. Then, my function is called, displaying the values of global var and local var within the function's scope. However, attempting to print local var outside the function scope will result in either nil or an error because local var is not accessible outside the function. This code illustrates the concept of variable scope in Lua, distinguishing between local and global scope within the context of functions. It begins by declaring a global variable and defining a function. Inside my function, a local variable is declared. Both global var and local var are then printed within the function's scope, showcasing local variable isolation. When my function is invoked, it displays the values of global var and local var within the function's local scope. However, attempting to access local var outside the function will result in either nil or an error, depending on the context. This highlights the concept of local scope, where variables are confined to the function in which they are defined and cannot be accessed from outside that function's scope. Conversely, global variables like global var can be accessed and modified from anywhere in the Lua script. In this specific case, when printing outside the function scope, we are using a comma to separate the string and the variable. This is necessary to avoid an error because the variable local var is not accessible outside the function scope. It would indeed provoke an error because local var is not defined outside the function scope, resulting in a concatenation attempt between a string and a nil value. Using a comma instead ensures that the variable is properly separated from the string in the print statement, and if the variable is nil, Lua handles it gracefully without throwing an error. Let us examine the outcome if we replace the comma with concatenation in the print statement when attempting to access local var outside its scope. When dealing with situations where accessing variables outside their scope might lead to errors, error handling mechanisms provide alternative solutions. Instead of causing the script to crash, error handlers like pcall and xpcall allow us to anticipate potential issues and handle them gracefully. By wrapping the code that might trigger an error inside a pcall or xpcall block, we can catch any errors that occur and execute alternative actions, such as displaying an error message or performing cleanup operations. This approach helps ensure the stability of the program and provides a smoother user experience by preventing abrupt script termination. We are using the pcall function, which stands for protected call. It allows us to call a function and handle any errors that may occur during its execution. Inside pcall, we provide an anonymous function as a parameter. This function contains the code we want to execute, which in this case is attempting to print the value of local var outside its scope. The result of pcall is assigned to two local variables, success and error message. Success will be true if the function executed successfully and false if an error occurred. The variable error message will contain the error message if an error occurred. If success is false, indicating that an error occurred during the execution of the anonymous function, we print an error message. In summary, we are using pcall to execute a piece of code, an anonymous function, and handle any errors that may arise during its execution. Pcall is a built-in function that allows you to call another function while handling any errors that may occur during its execution. The primary purpose of pcall is to execute a function and catch any errors that occur, preventing them from causing the script to crash. Pcall takes two parameters, a function to execute and any arguments that the function requires. It returns two values, a Boolean indicating whether the function executed successfully, true if successful, false if an error occurred, and the return values of the function or the error message if an error occurred. If the function executed successfully, pcall returns true along with the return values of the function. If an error occurred during the execution of the function, pcall returns false along with the error message. Pcall is a powerful tool in Lua for executing functions and managing errors, ensuring the stability and robustness of Lua scripts. The error message printed inside the pcall block can serve multiple purposes. It can provide a clear and informative error message for the user, explaining what went wrong and how to resolve the issue. This helps improve the user experience by guiding them through potential problems. It can also be useful for debugging purposes, especially during development. Printing the error message allows developers to quickly identify and address any issues in the code. Depending on the context, the error message can serve both purposes simultaneously. It can inform the user about the error while also providing valuable information for debugging purposes. xpcall is another error handling function in Lua. It stands for Extended Protected Call. The purpose of xpcall is the same as pcall, to execute a function and handle any errors that may occur during its execution. However, xpcall provides additional flexibility by allowing you to define a custom error handler function. Like pcall, xpcall takes two parameters, the function to execute and any arguments required by that function. In addition, xpcall takes a third parameter, the error handling function to be called in case of an error. If the function executed successfully, xpcall returns true along with the return values of the function. If an error occurred during the execution of the function, xpcall returns false along with the error message. The error handling function specified as the third parameter is then invoked to handle the error. In the provided code snippet, xpcall is used similarly to pcall to execute an anonymous function that attempts to print the value of local var outside its scope. However, instead of directly handling the error within the xpcall block, a custom error handling function is provided to handle the error. Here are the main differences between pcall and xpcall in Lua. pcall only provides basic error handling functionality. It catches errors and returns a Boolean indicating success or failure. xpcall allows you to specify a custom error handling function. This function is called in case of an error, providing more control over error handling behavior. pcall returns true if the function executes successfully and false if an error occurs. If an error occurs, the error message is returned as a separate value. xpcall returns true if the function executes successfully and false if an error occurs. If an error occurs, xpcall returns false along with the error message. The custom error handling function specified in xpcall is then invoked to handle the error. pcall, simpler to use for basic error handling scenarios where a custom error handling function is not required. xpcall provides more flexibility and control over error handling, but requires specifying a custom error handling function, making it slightly more complex to use. pcall, limited in terms of error handling options. It's suitable for simple error detection and handling scenarios. xpcall offers extended error handling capabilities, making it suitable for more complex error handling scenarios where custom error handling behavior is necessary. Mastering these concepts allows you to write more robust and maintainable code, leading to fewer bugs and smoother execution of your Lua scripts. Knowing how variable scope works helps you organize your code more effectively and prevents unintended side effects. It enables you to encapsulate data within specific parts of your program, improving readability and maintainability. Learning how to handle errors gracefully is essential for writing reliable Lua scripts. Proper error handling ensures that your programs can recover from unexpected situations, preventing crashes and providing better user experiences. By gaining proficiency in variable scope and error handling, you will be better equipped to tackle real-world Lua programming challenges and build more robust and resilient applications. Keep practicing and exploring these concepts to enhance your Lua programming skills further. At this tutorial, we will continue to explore the versatility and power of user-defined functions in Lua. We will begin by delving into several arithmetic functions that will lay the groundwork for creating a simple calculator. Let us begin by understanding how to define and utilize these functions to perform basic arithmetic operations. This knowledge will serve as a solid foundation for building more complex functionality. Using parameters allow us to pass values into functions when we call them, enabling the function to perform operations on different data each time it is invoked. In the context of our arithmetic functions, parameters like x and y allow us to perform addition, subtraction, multiplication, and division on different numbers depending on what values we pass in. This flexibility makes our functions more versatile and applicable to a wide range of scenarios, such as creating a simple calculator where users can input different numbers for calculations. When we divide a number by 0, it is mathematically undefined, and attempting such an operation would typically result in an error. In programming, we want our code to be resilient and handle such cases gracefully, rather than crashing or producing unpredictable results. By checking if y is equal to 0 before performing the division operation, we can prevent the program from encountering an error. Instead of allowing the division operation to proceed, which would result in a mathematical error, we provide a meaningful error message indicating that a division by 0 has occurred. This approach enhances the reliability and usability of our code. It ensures that even if the user provides unexpected input, the program will not crash abruptly but will instead inform the user of the issue in a clear and understandable way. Handling division by 0 is a common scenario encountered in programming, especially in situations where mathematical operations are involved. Dividing by 0 is mathematically undefined, and attempting such an operation can lead to errors or unexpected behavior in a program. Therefore, it is a good practice to include checks for division by 0 in your code whenever division operations are performed, to ensure that the program behaves predictably and provides meaningful feedback to the user in case of invalid inputs. This helps make the code more robust and user-friendly. The next part of the code allows the program to interact with the user by prompting them to input values and choose an operation to perform. We are prompting the user to provide input for the first number, the operation they want to perform, and the second number. We use tonumber function to convert the user's input into numerical values. This ensures that we can perform mathematical operations with the input. If the conversion fails, for example, if the user enters text instead of a number, tonumber returns nil. In that case, we use tonumber either read or 0 to provide a default value of 0, ensuring that we have valid numerical inputs to work with. By including tonumber and providing default values of 0, we ensure that our program does not break if the user provides unexpected input. It is a way to handle potential errors or invalid inputs gracefully. In essence, this part of the code allows our program to interact with the user, gather necessary input for mathematical operations, and handle potential errors or unexpected input smoothly. Now let us break down the final step. We use if, Elseif, and else to create a series of conditional statements based on the operation chosen by the user. The if statement checks if the operation variable is equal to plus. If it is, it executes the code block inside the if statement, which calls the add function with the provided numbers a and b and prints the result. If the operation is not plus, the Elseif statements check for other operations and execute the corresponding code blocks accordingly. If the operation does not match any of the expected values, the else block is executed, printing an error message indicating that the operation is invalid. Each code block within the conditional statements uses print to display the result of the operation, along with the appropriate message. Overall, this block of code determines which mathematical operation to perform based on the user's input, operation, executes the corresponding function, and prints the result. If the user provides an invalid operation, it informs them of the error. Note: in the defined functions, the parameters are named x and y. However, when we interact with the user and gather input, we assign those inputs to variables named a and b. This naming difference is just a matter of convenience and clarity in the code. When defining the functions, x and y are generic names for the parameters, indicating that the functions can accept any numerical values. When interacting with the user, a and b are used to represent the specific numbers provided by the user for the calculation. Using different variable names for the user input and the function parameters helps make the code more readable and understandable. It clearly distinguishes between the generic parameters used within the functions and the specific values provided by the user. In Lua programming, reusing functions is a fundamental concept known as function abstraction or modular programming. It involves creating functions that perform specific tasks and can be called multiple times throughout your code. This approach enhances code readability, reduces redundancy, and simplifies maintenance. You can achieve function reuse by defining functions with parameters that can vary each time the function is called, allowing for flexibility and versatility in your code. Additionally, Lua supports the creation of modules, which are collections of related functions that can be reused across different projects by importing them into your code. Function abstraction allows you to break down complex tasks into smaller, manageable units of functionality. By encapsulating specific tasks within functions, you can isolate and focus on solving individual problems, making your code easier to understand and maintain. Reusable functions with descriptive names improve the readability of your code. By abstracting away implementation details behind function calls, you can express the intent of your code more clearly, making it easier for other developers, including your future self, to understand and work with the codebase. Instead of duplicating code for similar tasks across your program, function abstraction enables you to define reusable functions that can be called multiple times. This reduces redundancy, minimizes errors, and promotes consistency throughout your codebase. Functions with parameters provide flexibility, allowing you to customize their behavior based on different inputs. This versatility makes your code more adaptable to changing requirements and facilitates scalability as your project grows in complexity. By organizing your code into modular functions, you create logical units that can be independently tested, debugged, and updated. This simplifies the maintenance process, as you can focus on fixing or enhancing specific functions without affecting other parts of the codebase. In summary, function abstraction in Lua programming empowers developers to write cleaner, more organized, and more maintainable code. By embracing modular design principles and leveraging the power of reusable functions, you can streamline development workflows, improve code quality, and build robust software solutions. In this tutorial, we will explore the concept of closures in Lua through a practical example. Closures are a powerful feature in Lua that allow functions to retain access to variables from their containing scope, even after that scope has exited. We will delve into 3 different counting functions, counter A, counter B, and counter C, each showcasing a unique aspect of closures. By the end, you will have a solid understanding of how closures work in Lua and how they can be utilized in your own projects. First, we define a function named counter A. This function does not take any parameters. Inside the counter function, we declare a local variable named count and initialize it to 0. This count variable will be used to keep track of our counting. We then have a for loop that iterates from 1 to 5. In each iteration of the loop, we increment the count variable by 1 using count equal to count plus 1. We print the current value of count and finally, we call the counter function. This execution of the function causes it to go through the steps defined above, resulting in the count from 1 to 5 being printed along with counter in front of each number. In summary, counter is a user-defined function that encapsulates a for loop. It defines a specific behavior, counting from 1 to 5 and printing each count along with a label. This encapsulation allows you to easily reuse this behavior whenever you call the counter function in your code. Next, we defines a function named counterb. Inside this function, it initializes a local variable count to 5. The counterb function returns an anonymous function. This returned function captures the count variable from its containing scope due to closure. Inside the returned function, it increments the count variable by 1. Then, it returns the new value of count, calls the counterb function and assigns the returned function to the variable b. Executes a for loop that iterates from 1 to 5. In each iteration, it calls the function stored in the variable b, which increments count and returns its value. Prints the current value of count after incrementing, along with the string counterb. So, in summary, counterb is a function that returns another function. The returned function has access to the count variable from its enclosing scope and increments it each time it is called. Then, the main block calls this returned function 5 times and prints the increment values. Counter is called only once because the loop is encapsulated within the function itself. Each time you call counter it executes the loop inside it, counting from 1 to 5 and printing the values. In contrast, counterb is called once to obtain the inner function, which is then called 5 times in a loop. Each time the inner function is called, it increments the count variable and returns its value, effectively counting from 6 to 10 and printing the increment values. In counterb, the returned function forms a closure by capturing and retaining access to the count variable declared in the enclosing scope of counterb function. This allows the inner function to maintain and increment the count variable across multiple calls, creating a persistent state between function invocations. We start by copying the structure of counterb to create counterc. We add a parameter starter to counterc, which allows us to specify the starting value of the count. Initializing the count variable inside counterc, we initialize the count variable with the value of the starter parameter. This means that the count will start from the value provided as an argument when calling counterc. The returned function from counterc still behaves the same way as the one from counterb, incrementing the count each time it is called. When calling counterc with parameter 10, for example, the count will start from 10 instead of 5 as in counterb. This modification allows for more flexibility in choosing the starting value of the count. So, in summary, by adding a parameter to counterc, we enhance its versatility by allowing users to specify the initial count value, providing more control over the function's behavior. Our last function counter serves as an example of function composition, combining all 3 counting functions in one place. Because of the different scopes of counter A, counter B, and counter C, different variables are used to call each function within counter all. This highlights the modular nature of functions in Lua and how they can be composed together to achieve more complex behaviors. Counter all demonstrates how to utilize and compose multiple functions together, each with its own scope and behavior, to achieve a desired outcome. Closures grant functions access to variables from their enclosing scope, even after that scope has exited. In simpler terms, a closure closes over or captures variables from the environment in which it was defined, allowing the function to retain and manipulate those variables later on. This feature is particularly useful for creating functions with persistent state, as demonstrated in our examples. By capturing and retaining variables from their surrounding scope, closures enable functions to maintain state across multiple calls, making them powerful tools for managing data and behavior in Lua. This tutorial provided a practical exploration of functions and loops in Lua, showcasing their utility in various scenarios. Through examples such as counter A, counter B, and counter C, we demonstrated how functions can be used to encapsulate behavior, while loops allowed for repetitive execution. Additionally, the concept of closure was introduced, highlighting its role in combining functions and retaining state across multiple calls. We also explored function composition, exemplified by the counter all function, which combines multiple functions to achieve complex behaviors. By understanding these fundamental concepts, Lua developers can enhance their ability to write modular, efficient, and flexible code. In this tutorial, we will explore the concept of functions and how they can be utilized to handle user input effectively. Specifically, we will learn how to define functions that prompt users for input. Explore how to use functions to process user input and produce meaningful output. Gain insight into nested functions and scope in Lua. Our scripts start with the function askName that prompts the user to input their name, reads the input from the console, assigns it to a variable named name, and then returns the value of name. Next, the function checkName takes a parameter name, which represents the user's name. It checks if the provided name is either empty or nil. If it is, meaning the user did not input anything, the function assigns the value stranger to name. After that, it prints a message welcoming the user by their name. In this case, input.upper is used to convert the user's input to uppercase letters before passing it to the checkName function. This ensures that the name is displayed consistently in uppercase letters, regardless of how it was entered by the user. So, when checkName is called with input.upper, it receives the user's name in uppercase format, checks if it's empty or nil, assigns stranger if necessary, and prints a greeting message. The input.upper syntax is a shorthand way of calling the upper function on the input string. In Lua, this is known as syntactic sugar, which means it's a convenient way of writing code that performs a common operation. So, instead of explicitly calling string.upper input, we can use the input.upper syntax, which achieves the same result more concisely. This syntactic sugar enhances readability and makes the code more intuitive, especially for new Lua learners. The askAge function prompts the user to input their age and reads the input from the console. It then checks if the input age is either empty or cannot be converted to a number using tonumber, age equal to nil. If either condition is true, meaning the user did not input anything or the input could not be converted to a number, the function assigns the value unknown to age. If the input is not empty and can be converted to a number, the function converts it to a numeric value using tonumber, age, and assigns it back to age. After handling the input, the function returns the value of age. In the subsequent code, the askAge function is called to obtain the user's age, and the returned value is stored in the variable age. Finally, a message is printed to the console, informing the user of their age. In programming, functions are blocks of code that perform specific tasks. They can accept inputs, process them, and produce outputs. When we use functions with inputs, we are essentially passing data into the function to be processed. Inputs can be provided in various forms, such as parameters passed directly to the function or inputs obtained from external sources like user input. In the provided example, the functions are used to handle user input. These functions prompt the user for information, process the input, validating and formatting, and return the processed data for further use. In summary, functions with inputs enable us to create reusable and modular code that can interact with external data, such as user input, to perform specific tasks efficiently. Nested functions are functions that are defined within the scope of another function. This means that the inner function is enclosed within the outer function and can only be accessed or called from within the outer function. The concept of nested functions allows for modularization and encapsulation of functionality within a specific context. This means that the inner function has access to the variables and parameters of the outer function, enabling it to perform tasks that are related to the outer function's purpose. Nested functions are particularly useful when you need to perform a task that is only relevant within the context of a particular function. By defining the inner function within the scope of the outer function, you can keep your code organized and reduce namespace pollution, as the inner function is only visible and accessible within the scope of the outer function. Functions can be declared using the local keyword, which restricts their scope to the block in which they are defined. When a function is declared as local, it can only be accessed within the same block of code where it is defined. The use of local functions helps to encapsulate behavior within a specific scope, preventing unintended interactions with other parts of the program. This means that local functions are only visible and accessible within the block of code where they are defined, making it easier to reason about and debug the code. Local functions are particularly useful when you want to define helper functions or utility functions that are only relevant within a specific context. By declaring these functions as local, you ensure that they are not accessible from other parts of the program, reducing the risk of naming conflicts and unintended side effects. Lambda functions, also known as anonymous functions or function literals, are a powerful feature found in many programming languages. They allow you to define a function without giving it a name, typically for short and simple operations. Lambda functions are often used in situations where you need to pass a function as an argument to another function, or when you want to create a quick, one-off function without the overhead of defining a named function separately. In many languages, lambda functions are expressed using a concise syntax. While Lua does not have built-in support for lambda functions with a dedicated syntax like some other languages, you can achieve similar functionality using anonymous functions defined with the function keyword. In Lua, you can create anonymous functions by defining a function without giving it a name and assigning it to a variable. Additionally, Lua's first-class functions allow you to pass functions as arguments to other functions, making it easy to use anonymous functions in situations where you need to pass a function dynamically. In the following sections, we'll explore how to use anonymous functions in Lua, including passing them as arguments and creating higher-order functions. The code snippet defines a function called apply operation that takes 3 arguments, func, x, and y. Apply operation is the name of the function being defined. Function, func, x, y, declares an anonymous function with 3 parameters, func, x, and y. Return func, x, y. Inside the function body, it calls the function func with arguments x and y and returns the result. The main idea behind this function is to provide a generic way to apply any operation, represented by the func parameter, to 2 values, x and y. By passing different functions as the func argument, you can apply various operations to x and y. This is a common pattern in functional programming and can be useful for creating more flexible and reusable code. Next block of code defines a function named add that takes 2 parameters, x and y, prints a message, and returns the sum of the parameters. The third block of code creates a function called add_anon using an anonymous function. The function does the same thing as the previous one. It adds 2 numbers together and prints a message. The key difference is that this function is assigned to a variable add_anon using the local keyword. Unlike the named function in the previous block, this function doesn't have a name itself. It is assigned to a variable instead, means it is an anonymous function. They are often used as arguments to other functions, especially when you need to pass a small piece of code as a parameter. This is commonly seen in scenarios like event handlers, callbacks, and higher-order functions. Additionally, anonymous functions can be useful when you want to create a function on the fly without giving it a specific name, especially if the function is only going to be used in a limited scope. They can help keep the code concise and focused. At last, the code calls a function named apply operation twice. Once with the add function and once with the add_anon function. It passes 2 numbers to each function and prints the result along with a message. A higher-order function is a function that can take other functions as arguments and/or return functions as results. In the provided code, apply operation becomes a higher-order function because it accepts a function, either add or add_anon, as one of its arguments. This allows apply operation to operate on different operations dynamically, making it more versatile and reusable. By passing either the add or add_anon function as an argument to apply operation, we are essentially giving apply operation the ability to perform different operations depending on which function is passed to it. This flexibility is a hallmark of higher-order functions, allowing for more modular and abstracted code. It is quite common to use anonymous functions with higher-order functions in Lua. Anonymous functions provide a convenient way to pass short, simple pieces of code directly as arguments to higher-order functions, without the need to define named functions separately. This practice is particularly useful for scenarios where the function being passed as an argument is only needed in a specific context and does not warrant a separate declaration. You can use named functions in the same way as anonymous functions when working with higher-order functions. The choice between using a named function or an anonymous function often depends on factors like code readability, reusability, and personal preference. Using a named function might be preferable if the function being passed as an argument is more complex or if you plan to reuse it in multiple places within your codebase. It can also make debugging easier since named functions provide more descriptive stack traces. On the other hand, anonymous functions are convenient for short, one-off operations that do not warrant a separate function definition. They can help keep the code concise and focused, especially when the function's purpose is clear within the context where it is used. Ultimately, both named and anonymous functions have their place in Lua programming, and the choice between them depends on the specific requirements and style preferences of your codebase. Welcome back to our Lua tutorial series. In the last few tutorials, we have been working with custom functions using positional arguments. Today, we will transition from custom functions to using tables for named arguments, making our code more flexible and readable. The function customer takes one parameter, name, and prints it. If name is not provided when calling the function, it defaults to unknown. The function customer expects one parameter, name. If name is not provided or is nil, it defaults to unknown using the OR operator. The function prints the value of name with the label name. When calling the function customer, you need to provide a value for the name parameter. However, if you call the function without providing a value for name, the default value unknown is used for name. To add more parameters to the customer function, such as age and city, you can simply extend the function definition to accept these additional parameters and adjust the default values accordingly. Now, the function customer accepts three parameters, name, age, and city. If any of these parameters are not provided when calling the function, default values will be used, unknown for name and city, and 0 for age. When calling the customer function, you need to provide values for all three parameters. If you call the function without providing values, the default values will be used. This modification allows the customer function to handle additional parameters while still providing default values for any that are not explicitly provided. When calling the customer function with positional arguments, it is important to ensure that the arguments are provided in the correct order, corresponding to the parameters in the function definition. For example, the first argument corresponds to name, the second to age, and the third to city. Positional arguments must be provided in the same order as the parameters in the function definition. If the order is incorrect, the arguments will be assigned to the wrong parameters, potentially leading to unexpected behavior or errors. If you want to omit one or more parameters and only provide values for certain ones, you need to remember the correct order and position of the parameters you want to skip. This can be error-prone, especially in functions with many parameters. Functions with many parameters can become less readable because readers need to remember the order and meaning of each parameter, especially if the function is called in multiple places with different arguments. In contrast, named arguments provide a solution to these limitations by allowing you to specify which parameter each argument corresponds to, regardless of the order in which they are provided. This makes the function calls more explicit, readable, and less error-prone. In this modified version, the customer function takes a single parameter info, which is expected to be a table containing the customer information. This table contains named arguments, name, age, and city, which are then unpacked inside the function to obtain the corresponding values. This approach allows for more flexibility and readability when calling the function, as you can specify the arguments in any order and explicitly label them. It also helps avoid confusion about the order of parameters, which is a limitation of using positional arguments. To define a function, we use parentheses after the function name to indicate its parameters, if any. To call a function, we use parentheses after the function name to provide arguments, if any, to the function. To create a table, we enclose the key-value pairs inside curly brackets to define a table. To pass a table as an argument, we can pass a table as an argument to a function by enclosing it in curly brackets. Positional arguments are passed to a function in a specific order, and their positions determine which parameter they correspond to in the function definition. Used when calling functions where the order of arguments is important and known. Arguments are assigned to parameters based on their order. Commonly used in functions where the order of arguments is consistent and known, such as mathematical functions or simple utility functions. Suitable for functions with a small number of parameters where the order is intuitive. Named arguments are passed to a function as key-value pairs, where the keys correspond to parameter names in the function definition. Used when calling functions where the order of arguments may not be important or when providing arguments selectively. Arguments are explicitly labeled with parameter names, allowing for flexibility in argument order. Used in functions where the order of arguments may vary or when providing arguments selectively is desirable. Useful for functions with many parameters or optional parameters, as they improve code readability and maintainability. Understanding the difference between positional and named arguments allows you to choose the appropriate method based on the requirements of your function and the readability of your code. Lua supports both approaches, providing flexibility in function argument passing. Coroutines are a powerful feature that allows you to perform cooperative multitasking. Unlike threads in many other languages, coroutines are not preemptive. They run until they yield control back explicitly. This can be particularly useful for implementing tasks that can be paused and resumed, like generators, iterators, or state machines. A coroutine in Lua is similar to a thread, but with the ability to yield control at certain points and be resumed later. This makes them lightweight and easier to manage compared to traditional threading models. Lua provides a set of functions to work with coroutines. Coroutine create creates a new coroutine with the specified function. Coroutine resume resumes a suspended coroutine optionally passing arguments. Coroutine yield yields control back to the coroutine's caller, optionally returning values. Coroutine status returns the status of the coroutine running, suspended, normal, or dead. Coroutine wrap creates a coroutine and returns a function that resumes it. Coroutines allow the myCoroutine function to pause and resume its execution. This is useful for scenarios where you need to manage long-running tasks, break down complex operations into smaller steps, or create custom control structures like iterators. Instead of running to completion in one go, the coroutine can yield control back to the main program, improving manageability and responsiveness. By default, a coroutine is not active by itself. When you create a coroutine using coroutine create, it starts in a suspended state and does not execute any part of the function until it is explicitly resumed with coroutine resume. The initial state it is suspended after creation. The activation requires explicit coroutine resume to start or continue execution. To control the flow, pauses with coroutine yield and resumes with coroutine resume. Ends in a dead state when the function completes. Let us see how the control flow works in this coroutine example and what it means. Control flow refers to the order in which individual statements, instructions, or function calls are executed or evaluated. In traditional programming, this flow is typically linear and controlled by constructs like loops, conditionals, and function calls. With coroutines, control flow becomes more flexible and can be paused and resumed, allowing for cooperative multitasking and more complex flow patterns. When my coroutine is first resumed, it will run until it hits this line. Local A, B, assigned to coroutine yield. It yields control back to the caller and returns first yield to the caller of coroutine resume. The coroutine pauses, waiting for the next coroutine resume call, which will provide values for A and B. When the coroutine is resumed, it continues execution. It prints the values of A and B that were passed to coroutine resume. After the first print, the coroutine hits this line. Local C, D, assigned to coroutine yield. It yields control back to the caller again and returns second yield to the caller of coroutine resume. The coroutine pauses again, waiting for the next coroutine resume call, which will provide values for C and D. When the coroutine is resumed, it continues execution. It prints the values of C and D that were passed to coroutine resume. Let us go through the process with an example of how this coroutine is used. Co-assigned to coroutine create, my coroutine. It creates a coroutine from the myCoroutine function. The coroutine is in a suspended state and has not yet started executing. Next, the first resume starts the coroutine. The coroutine runs until it hits the first coroutine yield. It yields first yield and pauses. The main program captures the result first yield and prints it. The coroutine resumes from the first yield, assigning hello to A and world to B. Next, the coroutine hits the second coroutine yield and pauses, yielding second yield. The main program captures the result second yield and prints it. The coroutine resumes from the second yield, assigning Lua to C and coroutines to D. The function completes execution, so the coroutine becomes dead. In summary, the coroutine uses coroutine yield to pause execution and return a value to the caller. Each coroutine resume call resumes the coroutine from where it left off and can pass values into the coroutine. Coroutines maintain their state between resumes, allowing complex sequences of operations to be broken down into manageable steps. The control flow is explicitly managed by the programmer, providing precise control over when and how code is executed. At the following example, the function range iterator takes three parameters: start, stop, and step. It returns a wrapped coroutine. Inside coroutine wrap, an anonymous function is defined. This function contains a for loop that iterates from start to stop with the specified step. Inside the loop, coroutine yields each value of I to the caller. The range iterator function with parameters 1, 10, and 2 creates the coroutine and returns a function that can be used as an iterator. This iterator function, when called, resumes the coroutine and returns the next yielded value. The generic loop for number in range iterator with parameters 1, 10, and 2 uses the iterator function to iterate over the yielded values. Each iteration calls the iterator function, which resumes the coroutine, yielding the next number in the sequence. The loop continues until the coroutine completes and no more values are yielded. In conclusion, coroutines in Lua provide a powerful mechanism for managing asynchronous tasks, creating custom iterators, and implementing cooperative multitasking. By understanding how coroutines work and how to use them effectively, you can enhance the flexibility and efficiency of your Lua programs. Experiment with coroutines in different scenarios to unlock their full potential and take your Lua programming skills to the next level. This code defines a function named worker which represents a coroutine. Within this function, there's a loop that runs 5 times. In each iteration, it prints a message indicating that the worker coroutine is running, along with the current step number. Additionally, it checks if the coroutine is currently running and prints a message if it is. After each iteration, it yields control back to the main program using coroutine yield. After defining the worker function, the code creates a new coroutine using coroutine create and assigns it to the variable co. This coroutine is created but not yet started. Coroutine status retrieves the current status of the coroutine, co. The status can be one of several values: running, suspended, normal, or dead. The if statement checks if the status of the coroutine is suspended. If the coroutine is indeed suspended, it prints a message. This code defines a function named resume coroutine that attempts to resume a coroutine and handles potential errors. Resume coroutine is defined locally and takes a single argument co, which represents the coroutine to be resumed. Inside the function, a coroutine is called, which attempts to continue the execution of the coroutine, co, from where it was last yielded. It returns two values. Status, a Boolean indicating whether the resumption was successful. And error, an error message if the resumption failed. The if not status statement checks if status is false, indicating that resuming the coroutine failed. If the resumption failed, it prints an error message. The underscore in the following loop is used as a throwaway variable. This means that the loop variable is not used inside the loop body, and the underscore is a convention to indicate that the variable is intentionally ignored. The underscore acts as a placeholder for the loop variable. It shows that you do not need to use the loop variable within the loop body. While you cannot technically write a loop without a variable in Lua, using the underscore is the closest equivalent. It tells anyone reading the code that the loop variable itself is not important. In essence, the underscore is used to iterate a specific number of times without needing to reference the loop variable inside the loop. The if statement checks if the status of the coroutine is not equal to dead. If the coroutine is not dead, it calls resume coroutine, co, to resume the coroutine. If the coroutine is dead, it means that the execution has finished successfully, and it prints a message. This ensures that the coroutine is resumed if it is still active, and acknowledges completion if it has finished. We have seen how to use coroutine running to determine if code is running within a coroutine. This is helpful for conditional behavior or error handling specific to coroutine execution. We have used the underscore as a placeholder in a loop, indicating that the loop variable is not needed within the loop body. This is a common convention in Lua when you do not intend to use the loop variable. We have implemented error handling for coroutine resumption using a custom function. This ensures graceful handling of errors that may occur during coroutine execution, providing better control and robustness in your code. These are essential techniques for effectively working with coroutines in Lua, enabling you to manage asynchronous tasks, control flow, and handle errors more efficiently. Tables are the only data structure in Lua that supports arrays, dictionaries, and records. They are essential for storing and organizing data, making Lua versatile for various applications, from configuration settings to complex data structures. Common use cases include: tables can be used to store lists, arrays, and collections of various data types. They also can map keys to values, allowing for the creation of dictionaries and other key-value pair structures. Tables are ideal for storing settings and configuration options in a structured and accessible manner. Often can be used to implement data structures like queues, stacks, graphs, and more. Tables can be also used to simulate objects and support object-oriented programming principles. The most basic form of a table in Lua is an empty table. An empty table is created by assigning a variable to a pair of curly brackets. In this example, my table is assigned to an empty table. This table does not contain any elements initially but can be populated with data later. Tables can be initialized with values. These values can be indexed numerically or with custom keys. In Lua, when you initialize a table with values directly within curly brackets, the values are automatically assigned numeric indices starting from 1. This is similar to arrays in other programming languages. The fruits table is initialized with 3 values: banana, orange, and cherry. Lua uses one-based indexing, meaning the first element is accessed with index 1, the second element with index 2, and so on. You can access each element of the table using its numeric index. Tables can also be initialized with key-value pairs. This allows you to create tables that act like dictionaries or associative arrays, where each value is associated with a specific key. The student table is initialized with 3 key-value pairs. Name is set to John. Age is set to 21. Major is set to computer science. You can access each value using its key, for example. Student.name returns John. Student.age returns 21. Student.major returns computer science. This approach allows you to create more complex data structures where each element is identified by a unique key, making your code more readable and easier to manage. Key-value pairs are particularly useful for representing structured data, such as the attributes of an object. When accessing values in a numerically indexed table, it is important to note that Lua uses one-based indexing. This means that the index of the first element in the table is 1, not 0 as in other programming languages. Numbers brackets 1 returns the first value in the table, which is 10. Numbers brackets 4 returns the fourth value in the table, which is 40. You can change the value of an element in the table by assigning a new value to its index. For example, numbers brackets 2 assigned to 25 changes the second value in the table from 20 to 25. After the change, print numbers brackets 2 returns the updated value, which is 25. This approach to indexing and modifying values in tables allows for straightforward and efficient data management, especially in applications requiring ordered data like lists or arrays. Tables can also act as dictionaries, where keys are used to access values. This allows for more flexible and descriptive data structures, where each value is associated with a specific key. The car table is initialized with 3 key value pairs. Make is set to Toyota. Model is set to Camry. Year is set to 2020. Values can be accessed using bracket notation or dot notation. You can change the value associated with a key by assigning a new value to it. Lua tables can store data as key-value pairs, allowing for more descriptive and flexible data structures. Values in a table can be accessed and modified using their keys, providing a convenient way to manage data in a table. This approach to using keys and values in Lua tables allows for efficient and descriptive data management, particularly in scenarios where each piece of data has a unique identifier or label. Tables serve as versatile data structures that can fulfill various roles, including arrays, dictionaries, and records. Understanding the basics of table creation, accessing, and modifying values is crucial for effective Lua programming. By mastering the fundamentals of Lua tables, programmers can efficiently manage data structures, streamline code, and create more robust and adaptable Lua applications. We will cover how to manipulate tables by adding, removing, and modifying elements, as well as using built-in table functions. You can add new elements to a table by directly assigning values to specific indices or by using the table insert function. In this example, we are adding an element to our table by using indices, and then we print the table using the built-in function table concat. The first line creates a table with 3 elements, 1, 2, and 3. Next line adds the value 4 at the 4th position of the table. Now, my table contains 1, 2, 3, and 4. The table concat function concatenates the elements of the table into a string, with each element separated by the specified delimiter, which in this case is a comma. So, the output will be 1, 2, 3, and 4. This example demonstrates how to add an element to a specific position in a table using indices and then print the table as a concatenated string using table concat. Instead of using indices, we can use a built-in function. By using table insert function, you can easily add elements to a table without having to manually manage indices, especially when you want to add elements at the end or in specific positions. This function call inserts the value 4 at the end of my table. If you want to insert the value at a specific position, you can provide a second argument specifying the position. By adding 2 as the second argument to the table insert function, we specify the position where the new value should be inserted. The third argument, 1.5, is the value to be inserted at that position. This allows us to easily insert elements at specific positions within the table without manually managing indices. We could use nil to remove an element from our table, but in this case, the table still has 4 elements, with one element being nil. When we use table concat, the presence of nil values can cause issues since table concat expects a sequence, meaning a table with no nil gaps between indices. When you want to remove an element from a table and maintain the integrity of the sequence, using table remove is the preferred approach. This function not only removes the specified element but also shifts all subsequent elements down by one position to fill the gap. This ensures that the table remains a proper sequence, which is important for functions like table concat that expect a contiguous array. You can modify existing elements by directly assigning new values to specific indices. When you use table sort function, Lua will sort the elements in ascending order. This works for numbers and strings, following their natural order, numerical for numbers and lexicographical for strings. You can provide a custom comparison function to change the sorting behavior. To sort the elements in descending order, you can provide a comparison function that returns true if the first element is greater than the second. Overall, understanding how to manipulate tables effectively is essential for writing clean and efficient Lua code, especially when dealing with complex data structures and algorithms. By mastering these techniques, you can harness the full power of Lua's table manipulation capabilities. This lesson covers different methods to iterate through tables, focusing on the differences between pairs and pairs, and how to use for loops to iterate over tables. Pairs function is used to iterate over all key-value pairs in a table, regardless of whether the keys are numerical or non-numerical. Pairs function is used to iterate over elements in a table with numerical indices starting from 1. It stops at the first nil value encountered. The pairs function allows you to traverse all key-value pairs in a table, which is especially useful for tables used as dictionaries. Note: it is normal for the output of the pairs function to be different each time you print the elements of a table in Lua. The pairs function iterates over all key-value pairs in a table, but the order in which the pairs are returned is not guaranteed to be the same every time. This is because Lua tables do not maintain a specific order for their elements when accessed using pairs. If you need to iterate over elements in a specific order, you'll need to manage the order yourself. One common approach is to store keys in an array and sort them before iterating. My table contains our key-value pairs. A new array keys is created, and all keys from my table are inserted into it using the pairs built-in function. The keys array is sorted alphabetically. The sorted keys are used to access and print the corresponding values from my table in a consistent order. In the provided example, we are using a generic for loop. In Lua, a generic for loop iterates over all values returned by an iterator function. Both pairs and pairs functions are examples of iterator functions. This way, you can control the order in which the elements are processed. The second loop iterates over a sorted list of keys from my table, using the underscore placeholder to ignore the index and directly access each key. It prints each key and its corresponding value from my table, ensuring a consistent, ordered output. The pairs function is suited for iterating over tables with consecutive numerical indices starting from 1, such as arrays. In this example, the indices are 1, 2, 3, and 4, which are consecutive and start from 1. Using the iPairs function to iterate over this table will visit each element in the order of these indices. This loop will print each index value pair in the array in the order of their indices, confirming that iPairs is ideal for tables with consecutive numerical indices. Another approach to iterate over elements in an array or a table with consecutive numerical indices is by using a numeric for loop. This loop gives you precise control over the indices and can be particularly useful when you know the range of indices you want to iterate over. The loop starts at I assigned to 1, which is the first index of the array. It continues as long as I is less than or equal to the length of my array. After each iteration, I is incremented by 1. In each iteration, the current index and the corresponding value are printed. Both iPairs and numeric for loops are suitable for arrays, but numeric for loops offer more control over the iteration process. Dictionary-like tables are those where keys are not necessarily numerical and can be strings or other types. Using the pairs function is ideal for dictionary-like tables where you want to iterate over all key value pairs, regardless of the key types. This makes pairs versatile for accessing elements in tables where keys are not consecutive numbers. My table is defined as a dictionary-like table with string keys, name, age, city, and their corresponding values, Alice, 30, Wonderland. The pairs function is used to iterate over all key value pairs in my table. In each iteration, k is assigned the current key, and v is assigned the corresponding value. The print k, v statement prints the current key and value. The output may vary in order because pairs does not guarantee the order of iteration. Pairs and iPairs functions, along with generic and numeric for loops, are indispensable tools in Lua for efficiently traversing and processing data stored in tables, catering to a wide range of use cases and programming scenarios. Lua provides several built-in functions to work with tables. Here, we will cover table pack and table unpack functions. The table pack function is used to take a variable number of arguments and pack them into a table. This is useful when you need to handle multiple values as a single table object. Table pack accepts any number of arguments. It creates a new table where each argument is stored in sequence. It also adds a special field n to the table, which stores the total number of arguments. The n field is essential because it provides a way to know exactly how many arguments were packed into the table. This is especially useful when some of the arguments might be nil, as simply checking the length of the table. Using the length operator might not give the correct count. Print t.n is specific to tables created by table pack function and provides a reliable way to get the count of packed arguments. Tables created with table pack behave like any other table when accessed and manipulated using bracket notation. This allows you to work with them seamlessly using familiar syntax and operations. Whether you are reading values, assigning new ones, or performing other table operations, you can use bracket notation with tables created by TablePack just like you would with any other Lua table. In Lua, if you create a table with nil values, the standard length operator will stop counting at the first nil. This can be problematic when you need to include nil values in your list. TablePack overcomes this by storing the number of elements explicitly. When a function returns multiple values, TablePack can be used to store these values along with the count, ensuring all values are preserved, even if they include nil. In summary, TablePack is particularly useful for preserving the structure and length of tables that include nil values, ensuring that all elements can be accessed and counted correctly. The table unpack function is used to return the elements of a table as multiple return values. This can be particularly useful when you want to pass the elements of a table as individual arguments to a function or when you need to assign multiple values at once. The function returns the elements of the table from the specified starting index, I, to the ending index, j. If I and j are not specified, it defaults to unpacking all elements from the first to the last. In this example, a table, T, is created with the elements 1, 2, 3, and true. Table unpack, T, returns the elements of the table as multiple values. These values are assigned to the variables a, b, c, and d. The output of print will be 1, 2, 3, and true. I and j parameters allow you to specify the range of elements to unpack. If you do not specify I and j, table unpack defaults to I assigned to 1 and j assigned to the length of the table. Understanding how to use the I and j parameters allows you to selectively unpack elements from a table, providing greater flexibility in managing table data. When you use table unpack on a table that contains nil values, it will include those nil values in the unpacked results. However, the presence of nil can affect the interpretation of the number of results, especially if you are using the unpacked values in a context that expects a specific number of results. You can specify the range of elements to unpack, and table unpack will still include nil values within that range. It is important to note that when nil values are present, they can affect the length of the result if you try to determine it by counting the non-nil values or using the length operator on the table directly. However, table unpack itself will correctly handle nil values and include them in the unpacked results. Using table unpack with tables that contain nil values requires understanding that nil values will be part of the unpacked results, which can be crucial for functions and contexts that expect specific numbers of arguments or results. Mastering the manipulation of tables is crucial for effective Lua programming. One powerful way to handle tables is by creating custom functions that can perform specific operations on them. These functions enhance code reusability, readability, and modularity, making your programs easier to manage and extend. In this tutorial, we will explore how to create custom functions to manipulate tables in Lua. We will cover 3 practical examples that demonstrate common operations. We define a custom function named SumTable that takes a single argument t, which is expected to be a table containing numerical values. We create a local variable sum and initialize it to 0. This variable will hold the cumulative sum of the elements in the table. We start a loop using ipairs to iterate over the table t. The ipairs function returns both the index and the value of each element in the table, but we only care about the value here, so we use underscore to ignore the index. Inside the loop, we add the current value to the sum variable. This accumulates the sum of all values as we iterate through the table. After the loop completes, we return the accumulated sum. We create a table named numbers containing the values from 1 to 5. We call the SumTable function with numbers as the argument and print the result, which is 15. This custom function, SumTable, provides a simple yet effective way to sum all numerical elements in a Lua table, showcasing the power and flexibility of custom table manipulation functions in Lua. In our next example, we define a custom function named filterTable that takes two arguments, t, the table to filter, and condition, a function that defines the condition to filter by. We create an empty table named newTable that will hold the elements that meet the condition. We start a loop using ipairs to iterate over the table t. The ipairs function returns both the index and the value of each element in the table, but we only care about the value here, so we use underscore to ignore the index once again. Inside the loop, we check if the current value meets the condition by calling the condition function with value as its argument. If the function returns true, the value meets the condition. If the condition is met, we insert the value into the new table using the table insert function. After the loop completes, we return the new table containing all the elements that met the condition. We create a table named numbers containing the values from 1 to 5. We call the filter table function with numbers and a condition function that checks if a number is even. We store the result in even numbers and print each value in even numbers, which are 2 and 4. This custom function, filterTable, allows you to create a new table that contains only the elements meeting a specified condition, demonstrating the flexibility of table manipulation in Lua. In our last example, we define a custom function named mapTable that takes two arguments. T, the table to be mapped, and func, the function to apply to each element. We create an empty table named newTable that will hold the transformed elements. We start a loop using iPairs to iterate over the table T. The iPairs function returns both the index I and the value of each element in the table. Inside the loop, we apply the function func to the current value and assign the result to the corresponding index I in newTable. After the loop completes, we return the new table containing all the transformed elements. Once again, we create a table named numbers containing the values from 1 to 5. We call the mapTable function with numbers and a function that squares each number. We store the result in squared numbers and print each value in squared numbers, which are 1, 4, 9, 16, and 25. This custom function, mapTable, allows you to apply a function to each element of a table and create a new table with the results, demonstrating the power and flexibility of functional programming in Lua. Welcome to our tutorial on nested tables. In this video, we will explore how to create and work with nested tables, which are powerful tools for organizing complex data. Whether you are handling matrices, simulating databases, or representing hierarchical structures, nested tables can make your code more efficient and easier to manage. Let us dive in and see how nested tables can enhance your Lua programming skills. Here, outer table is a table containing 3 nested tables. Each nested table, or inner table, contains 3 numeric values. To access the elements in these nested tables, you use 2 sets of square brackets. The first set specifies the index of the inner table, and the second set specifies the index of the element within that inner table. This example demonstrates how to create a nested table in Lua and access specific elements within it using indices. This technique is particularly useful for organizing and manipulating multi-dimensional data. Here, outer table is a table containing two nested tables identified by the keys row 1 and row 2. Each nested table contains key value pairs where A and B are the keys, and their corresponding values are numerical. To access the elements in these nested tables, you use dot notation. The first part specifies the key of the nested table, and the second part specifies the key of the element within that nested table. This example demonstrates how to create a nested table with named keys and access specific elements within it using dot notation. This method is especially useful for creating more readable and manageable data structures, as you can refer to elements by descriptive names rather than numerical indices. This loop iterates over each element in outer table. I is the index of the current element in outer table. Inner table is the nested table at the current index. This loop iterates over each element in the current inner table. J is the index of the current element in inner table. Value is the value of the current element in inner table. This statement prints the indices and the value of the current element. It constructs a string showing the current indices and the value. This example demonstrates how to iterate over a nested table using nested for loops. The outer loop iterates through the main table, and the inner loop iterates through each nested table, printing the indices and values of all elements. This technique is useful for examining or processing all elements in a nested table structure. The following example demonstrates how to represent a matrix using nested tables in Lua and how to access specific elements within the matrix. Matrices are essential for various computational tasks, including mathematical operations, graphics programming, and data manipulation. By organizing data in a matrix format, you can perform complex operations efficiently and clearly. Database is a table containing two nested tables, users and posts. The users table contains records with user information, ID, name, and age. The posts table contains records with post information, ID, user ID, and contents. This structure allows you to store and manage related data efficiently, simulating a simple database. To access specific elements within these nested tables, you use dot notation combined with index numbers. The example demonstrates how to simulate a simple database using nested tables in Lua. By organizing user and post data in separate nested tables, you can efficiently store and retrieve related data. This technique is particularly useful for applications requiring structured data storage and retrieval, such as content management systems or user databases. Company is a table representing a company with a name and a departments table. Departments is a nested table containing two key value pairs, IT and HR. Each department is itself a table of employees. Each employee is represented as a table with name and position. This structure effectively models a company's organization with departments and employees. To access specific data in this nested table, you use dot notation for the main table and nested keys and indices. This example demonstrates how to model hierarchical data using nested tables in Lua. By organizing the company's information into departments and employees, you can efficiently manage and retrieve data related to different parts of an organization. This approach is useful for applications requiring structured and categorized data, such as employee management systems or organizational charts. Nested tables are a fundamental concept in Lua, offering a flexible way to handle complex data. By mastering nested tables, you can efficiently manage multi-dimensional data, simulate database-like structures, and organize hierarchical information. Understanding how to create, access, and manipulate nested tables will enhance your ability to design and manage structured data in your Lua applications. In Lua, a table is a fundamental data structure that is often used as arrays, dictionaries, or even objects. Metatables are tables that can change the behavior of another table by defining how certain operations on the base table should behave. A metatable allows you to define custom behavior for operations such as addition, subtraction, concatenation, and more. To set a metatable for a table, you use the setMetatable function, and to retrieve it, you use the getMetatable function. This output confirms that the myMetatable was correctly set for my table, and getMetatable returns the same table as my metatable. The equal operator checks for reference equality, which in this case confirms that the metatable was correctly assigned. Metatables can define custom behavior through meta methods. A meta method is a function that is called when a specific operation is performed on a table. These operations can include arithmetic operations, table accesses, and more. You can use a metatable to provide default values for table keys that do not exist. In Lua, the double underscore prefix is used to denote special fields in tables, particularly meta methods in metatables. These special fields define behaviors that override or extend the default behaviors of tables. The double underscore index field is one of the most commonly used meta methods in Lua. In this example, whenever a key is accessed that does not exist in my table, the double underscore index meta method is called, which returns the string default value. Lua supports operator overloading using specific meta methods. These meta methods allow you to define how tables behave with arithmetic and relational operators. Vector is an empty table that will serve as a prototype for all vector objects. Vector sets the index meta method of the vector table to itself. This will be used for inheritance-like behavior. The new function is a constructor for creating new vector objects. It takes two parameters, x and y, which represent the coordinates of the vector. It creates a new table V with fields x and y. setMetatable sets the metatable of V to vector, enabling inheritance of methods defined in vector. The function returns the new vector object V. add function is defined to overload the addition operator for vector objects. It takes two vector objects, a and b, as arguments. It creates a new vector whose x and y components are the sums of the corresponding components of a and b. It returns this new vector by calling vector new. v1 is created as a vector with x assigned to 1 and y assigned to 2. v2 is created as a vector with x assigned to 3 and y assigned to 4. v3 is created by adding v1 and v2 using the overloaded addition operator. The vector table serves as a prototype for all vector objects, with methods like new and the overloaded double_add operator. The new function creates and initializes new vector objects. The double_add function enables the use of the addition operator to add two vector objects by defining custom behavior. New vector objects are created, added together, and the result is printed. This example demonstrates how to use metatables and meta methods in Lua to implement object-oriented features and operator overloading, providing a clear and concise way to work with custom data structures like vectors. My table is an empty table that will be the subject of our custom behavior. My meta table is another table that defines a special meta method, double_concat, which will customize the behavior of the concatenation operator. The double_concat function is called whenever the concatenation operator is used with my table. It takes two arguments, a and b, which are the operands of the concatenation. Tostring, a, converts a to a string if it is not one already. Tostring, b, does the same for b. The function returns the concatenation of the string representations of a and b. This sets my meta table as the meta table for my table. With this, any concatenation involving my table will use the custom double_concat function defined in my meta table. This code demonstrates how Lua's metatables and meta methods can be used to override and extend the behavior of built-in operators, providing flexibility in how custom types and data structures interact with these operators. The function read-only is defined, taking one argument table. A new empty table called proxy is created. This table will act as a proxy for the original table. A metatable MT is created with two fields. Field index is set to the original table. It means if a key is accessed in the proxy table that does not exist, Lua will look for it in the table. Field new index is set to a function that throws an error. This function is triggered when there is an attempt to modify the proxy table. The error function is called with the message attempt to modify a read-only table and a level 2 to indicate where the error occurred in the call stack. The setMetatable function sets MT as the metatable for the proxy table. This step makes the proxy table behave according to the rules defined in the metatable. The proxy table is returned from the read-only function. This table is now a read-only version of the original table. Original table is a normal Lua table with keys A and B. Read-only table is created by calling read-only original table. This read-only table behaves like original table but cannot be modified. When accessing read-only table.a, the index meta method is invoked. Since read-only table is empty, Lua looks up in the original table, returning 1. When attempting to set read-only table.a to 10, the new index meta method is invoked. This triggers the error, preventing the modification. By using this read-only function, you can create tables that protect their contents from being altered, ensuring data integrity in your program. A table myTable is created with two keys x with a value of 10 and y with a value of 20. MyMetaTable is defined with two meta methods. Index, this function is called whenever a key that does not exist in the table is accessed. It prints a message indicating which key is being accessed and then uses rawget to return the actual value from the table. New index, this function is called whenever a key is set to a new value. It prints a message indicating which key is being set to which value and then uses rawset to set the value in the table. The setMetaTable function is used to associate my metatable with my table. From this point on, my table will use the meta methods defined in my metatable. The key x is accessed from my table. Since x exists in my table, the index meta method is not triggered. The value 10 is printed. The key x is accessed again. Since x exists in my table, the index meta method is not triggered. The new value 30 is printed. When you access a key, Lua first checks if it exists in the table. If it does, Lua returns the value directly. If the key does not exist, Lua calls the index function in the metatable, which prints a message and retrieves the value using rawget. When you set a key, Lua calls the new index function in the metatable. This function prints a message and sets the value using rawset. In Lua, tables are the primary and only data structure that can be used to create arrays, dictionaries, and objects. Lua tables are highly flexible and can be used to simulate object-oriented programming principles. This allows you to create objects with properties and methods similar to those found in more traditional OOP languages like Java or Python. Tables can hold various types of data, including numbers, strings, functions, and even other tables. This makes them versatile containers that can represent complex structures. Mechanisms such as metatables and meta methods allow tables to behave like objects. By using these features, you can define custom behaviors for tables. Mechanisms such as metatables and meta methods allow tables to behave like objects. By using these features, you can define custom behaviors for tables. This code defines a table person with properties name and age, and a method greet that prints a greeting using the name property. The print statements show how to access the properties and call the method. Lua supports prototype-based inheritance using metatables. Here is an example of creating a class-like structure. Person is a table representing the class. Person index sets up person as its own metatable, enabling inheritance of its methods. Person new is a constructor function that creates a new instance of person. setMetatable sets the metatable of the new instance to person, allowing method inheritance. The name and age properties are set, defaulting to unknown and 0 if not provided. Person greet is a method that prints a greeting using the instance's name property. Person new creates a new person object with the name John Doe and age 30. John greet calls the greet method, outputting hello, my name is John Doe. Lua does not have built-in OOP syntax, but you can simulate it using tables and metatables. This involves creating constructors, defining methods, and using inheritance. Animal is a table representing the base class. Animal index sets up animal as its own metatable, enabling inheritance of its methods. Animal new creates a new instance of animal. The name property is set, defaulting to unnamed if not provided. Animal makes sound is a method that prints a message using the instance's name property. Dog is a table representing a subclass of animal. Set metatable makes dog inherit from animal. Dog index sets dog as its own metatable for its instances. Dog new creates a new instance of dog. It calls animal new to initialize the name property, then sets the breed property, defaulting to unknown breed if not provided. Dog makes sound overrides animal makes sound to provide specific behavior for dog. My dog assigned to dog new creates a new dog object with the name Buddy and breed Golden Retriever. My dog makes sound calls the overridden make sound method, outputting Buddy barks. Tables can represent real-world entities in games, simulations, or applications. This code defines a car class in Lua using tables and metatables to simulate object-oriented programming. Car is a table representing the class. Car index sets up car as its own metatable, enabling inheritance of its methods. Car new is a constructor function that creates a new instance of car. Set metatable sets the metatable of the new instance to car, allowing method inheritance. The brand and model properties are set to the values provided when the new instance is created. Car drive is a method that prints a message using the instance's brand and model properties. My car assigned to car new creates a new car object with the brand Toyota and model Corolla. My car drive calls the drive method, outputting the Toyota Corolla is driving. You can use tables to represent UI elements and their interactions. This code defines a button class in Lua using tables and metatables to simulate object-oriented programming. Button is a table representing the class. Button index sets up button as its own metatable, enabling inheritance of its methods. Button new is a constructor function that creates a new instance of button. Set metatable sets the metatable of the new instance to button, allowing method inheritance. The label property is set to the value provided when the new instance is created. Button click is a method that prints a message using the instance's label property. My button assigned to button new creates a new button object with the label submit. My button click calls the click method, outputting button submit clicked. Tables can be used to store complex data structures and perform operations on them. This code defines a data store class in Lua using tables and metatables to simulate object-oriented programming for storing key-value pairs. Data store is a table representing the class. Data store index sets up data store as its own metatable, enabling inheritance of its methods. Data store new is a constructor function that creates a new instance of data store. Set metatable sets the metatable of the new instance to data store, allowing method inheritance. The data property is initialized as an empty table to store key-value pairs. Data store add is a method that adds a key-value pair to the data table. Data store get is a method that retrieves the value associated with the given key from the data table. Data store new creates a new data store object. Store add adds the key-value pair, name, and Lua to the data table. Print retrieves and prints the value associated with the key, name, outputting Lua. Using tables to simulate objects in Lua provides a flexible and powerful way to apply object-oriented programming concepts in a lightweight scripting language. By leveraging tables, metatables, and custom functions, you can create robust and reusable code structures that mimic the behavior of classes and objects found in traditional OOP languages. Tables are incredibly versatile and can be used to create various data structures such as arrays, lists, dictionaries, stacks, and queues. We will overview how to implement these data structures using tables. Arrays in Lua are tables with numerical indices starting from 1. The following example creates an array with values 1 through 5. Loops through each index of the array and prints each element of the array during iteration. Lists are similar to arrays but are typically manipulated with functions to add or remove elements. The following snippet initializes a list with values 10, 20, and 30. Adds the value 40 to the end. Next, remove the last element from the list. Then iterates through each element. And at last it prints each value in the list during iteration. Dictionaries, or associative arrays, use non-numeric keys. The snippet create a dictionary with keys name, age, and profession and their respective values. Next, the code print the value associated with the key name, which is John. Iterates over each key value pair in the dictionary. And print each key and its corresponding value during iteration. Stacks follow the last in, first out principle. The code creates an empty table stack that will be used to store stack elements. Defines a method, push, that adds value to the end of the stack using table insert. Then defines a method, pop, that removes and returns the last element from the stack using table remove. Stack push adds 10 and 20 to the stack. At the end, print 20 and 10, respectively, showing the behavior of the stack. Queues operate on the first in, first out principle. The snippet start creating an empty table queue to represent the queue. Defines a method enqueue that adds value to the end of the queue using table insert. Next, defines a method dequeue that removes and returns the first element from the queue using table remove, which operates with an index of 1 to ensure first in, first out behavior. Next snippet creates simple inventory system. The system should support the following operations: adding an item, removing an item, and listing all items. It starts by creating an empty table inventory that will be used to store items. Defines a method, addItem, for the inventory table with parameters name and quantity. Then checks if the item already exists in the inventory. If item exists, increments the existing quantity of the item. If item does not exist, adds the item to the inventory with the specified quantity. In summary, this block of code allows you to add items to the inventory either by updating the quantity if the item already exists or by initializing it with a given quantity if it's new. The following function defines a method for the inventory table. It takes two parameters, name and quantity. Next checks if the item name exists in the inventory. Subtracts the specified quantity from the item's current quantity. If the updated quantity is 0 or less, it removes the item from the inventory by setting its value to nil. If item does not exist, prints an error message indicating that the item was not found in the inventory. In summary, this function removes a specified quantity of an item from the inventory. If the quantity drops to 0 or below, the item is deleted from the inventory. If the item does not exist, an error message is printed. Next function defines a method list items for the inventory table. This method is used to list all items and their quantities in the inventory. Then uses pairs, self, to iterate over all key value pairs in the inventory table. Here, name represents the item name and quantity represents its quantity. It checks if the quantity is of type number to ensure it is a valid inventory item. If true, it prints the item name and its quantity. The last part of the code provides a way to display the current inventory, showing each item and its corresponding quantity. We have explored using Lua tables to implement various data structures including arrays, lists, dictionaries, stacks, and queues. We applied these concepts to design and manage a simple inventory system, demonstrating how to add, remove, and list items effectively. Additionally, we covered techniques for manipulating tables, such as iterating over elements and defining functions for specific operations. This comprehensive approach provides a solid foundation for managing data and building applications in Lua. Efficient use of tables can significantly impact the performance and memory usage of your Lua scripts. We will explore best practices and optimization techniques for managing tables, focusing on memory management and common pitfalls. Table pooling is a technique used to reuse tables instead of creating new ones frequently. This helps in reducing memory allocation and garbage collection overhead. In that case, getTable retrieves a table from the pool if available, or creates a new one if the pool is empty. Next, return table clears the table's contents and returns it to the pool for future reuse. Use table pooling in performance-critical parts of your code where tables are frequently created and discarded. The memory leaks occur when tables are unintentionally retained, leading to excessive memory usage. If my table is not properly managed, it could lead to memory leaks. Ensure tables are cleared or set to nil when they are no longer needed, and use table pooling where applicable. Certain operations on tables can be inefficient if not properly managed. This function creates a new table temptable for each call, which might be inefficient if used frequently. Minimize table operations within performance-critical code and reuse tables where possible. Proper management of memory can reduce the overhead of garbage collection and improve performance. Set meta table creates a weak value table. This means that the values stored in this table will be garbage collected if no other references to them exist. Use weak tables for caching to ensure that memory is freed when the cache data is no longer needed. This line creates a default table with two key value pairs. Key 1 with the value default 1, and key 2 with the value default 2. When accessed, the values stored in the table must use their respective keys. Creating a new table in each iteration of the loop can be inefficient. Reuse tables when possible and avoid creating unnecessary tables inside loops. Understanding the difference between contiguous and sparse tables can help optimize performance. Sparse table contains non-sequential indices, which can be less efficient. Contiguous table contains sequential indices, which are generally more efficient for operations that involve array-like behavior. Use contiguous tables for sequences or array-like operations to ensure better performance. This code initializes an empty dynamic table and then populates it with values from 1 to 100 using a for loop and the table insert function. Setting dynamic table to nil allows the Lua garbage collector to reclaim the memory used by the table, which is important for efficient memory management. This example illustrates how to dynamically create and populate a table, and then properly manage memory by setting the table to nil when it is no longer needed. This helps avoid memory leaks and ensures your Lua programs run efficiently. Understanding and optimizing the use of tables can significantly enhance the performance and memory efficiency of your scripts. By following best practices such as table pooling, using weak tables, and managing memory proactively, you can write more efficient and robust Lua programs. Tables are a powerful feature, and mastering their use will greatly expand your programming capabilities. To get started with Lua modules, let us create a very simple module that prints Hello World when a function is called. Local m creates a local table that will hold our module's functions and variables. Next function defines a function hello within the module. Return m allow access by other Lua scripts that require this module. To use the module, you need to load it with the require function in another Lua script. Require loads my module and assigns it to the local variable my module. The require function looks for a file named myModule Lua in the search paths. This calls the hello function from my module, which prints hello world to the console. In Lua, you can define functions within a module that are either public, accessible from outside the module, or private, accessible only within the module. This distinction helps in encapsulating functionality and exposing only the necessary parts of your module. To use the module, create another Lua script that requires this module and calls the public function. Now let us create a practical utility module that performs file operations. This module will include a function to read the content of a file. Local table file utils will hold our module's functions. ReadFile defines a function that takes a file name as an argument. It attempts to open the file for reading. IOOpen attempts to open the file in read mode. If it fails, file will be nil and error will contain the error message. If the file cannot be opened, it prints an error message and returns nil. If the file is successfully opened, it reads the entire content of the file, then closes the file after reading. To use this utility module, create another Lua script that requires this module and calls the readFile function. Require loads the file utils module and assigns it to the local variable. Local content calls the readFile function from the file utils module, attempting to read the content of the test file. If content checks if the content is not nil. If it is not, it prints the content of the file. If it is, it prints a failure message. Metatables provide a powerful mechanism for customizing the behavior of tables. When used with modules, metatables can add advanced functionality such as inheritance, operator overloading, and custom method resolution. Local MT creates a metatable with an index field pointing to M. The index field is used to look up methods in the module table. Function mNew defines a constructor function that creates a new instance of the module. Local self creates a new table and sets its metatable to MT, effectively making it an instance of the module return self. This returns the new instance. Function mHello defines a method hello for instances of the module. The colon syntax automatically passes the instance, self, as the first argument. To use the module, once again we need another Lua script that requires this module, creates an instance, and calls the method. Require loads the module and assigns it to the local variable myModule. Local obj creates a new instance of the module by calling the new function. Obj_hello calls the hello method on the instance obj, which prints hello from metatable. Using metatables and modules allows you to create more sophisticated and flexible Lua modules, enabling patterns like object-oriented programming and custom behaviors. Modules are typically stored in specific directories and are loaded using the require function. Understanding how Lua searches for modules and how to manipulate these paths is crucial for effective module management. Lua uses two paths to search. Package path for Lua modules. Package C path for C modules. The default search paths are defined when Lua is compiled. You can add directories to the search path by appending them to package path or package C path. The semicolon is used as a statement separator, similar to many other programming languages. However, when it comes to modifying package path and package C path, the semicolon is used as a path separator within these strings. The question mark is used as a wildcard character in the module search paths. It is replaced by the module name when Lua searches for a module to load with require. Once the search paths are correctly set up, you can load modules using require. Lua will search through the paths specified in package path and package C path. Let us say you have a directory structure like this. To load a my module from a custom directory, you need to tell Lua where to find your custom module by adding the directory to package path. This allows Lua to locate and load the module when you use the require function. Next, use the require function to load the module. This tells Lua to search the directory specified in package path for the module file. After loading the module, you can call its functions or use its variables. For nested modules, ensure that your directory structure reflects the module's namespace. You can load init Lua by requiring my module and submodule Lua. This line adds the main directory and the nested module directory to package path. When working with nested modules in Lua, require helps you load specific parts of your module hierarchy. By managing package path and using the require function effectively, you can organize and load Lua modules from custom directories, as well as handle nested module structures with ease. Following these practices ensures your Lua projects remain modular, organized, and scalable. By correctly configuring package path and using require, you can manage dependencies and load modules efficiently, keeping your code base clean and maintainable. File handling allows scripts to interact with the file system by reading from and writing to files. This capability is essential for tasks like saving game progress, logging data, and reading configuration settings. Use the IOOpen function to open a file. You need to specify the file name and the mode. File modes. R. Read the file. The file must exist. W. Write the file. Creates a new file or truncates an existing file. A. Append to the file. Opens the file for writing, preserving existing content. R. Plus. It can read and write. The file must exist. W. Plus. It can read and write. Creates a new file or truncates an existing file. A. Plus. It can read and append. Opens the file for reading and writing, preserving existing content. After performing operations, close the file to release system resources. You can read the entire content or line by line. The *all argument used with file read is a special pattern that instructs the function to read the entire content of the file. It reads the entire file content as a single string. This is useful when you want to load the whole file into memory at once. Other patterns with file read are *n, it reads a number from the file. *l, it reads a single line from the file. *a, it reads all the remaining data from the current position to the end of the file. These patterns offer flexibility depending on the type and structure of data you're dealing with. This code snippet reads a file line by line and prints each line to the console. The approach is efficient for processing large files as it reads one line at a time rather than loading the entire file into memory. To write to a file, open the File in Write or Append mode. This code effectively demonstrates how to create or overwrite a file with specific content. This snippet appends data to an existing file. The code is useful for adding new content to a file without removing or modifying existing data. These basics allows you to perform essential file operations, whether for logging, data storage, or configuration management. With these skills, you can enhance your scripts to interact with the file system effectively and manage data persistence in your applications. An absolute path provides the complete path from the root of the file system to the target file or directory. When to use an absolute path? When you need to specify a file or directory that is always located in the same place, regardless of where your program or script is being run. When writing scripts or applications that require accessing system-wide resources or configurations. It is useful in contexts where the working directory might change, but the resource location needs to remain fixed. A relative path specifies the path to a file or directory in relation to the current working directory or another reference point. Does not begin with the root. Instead, it describes a path relative to the location where the script or command is executed. When to use a relative path? When working with files or directories within a project or application where the current working directory or project directory is predictable. This makes the path adaptable if the directory structure changes, but the relative positions remain the same. For scripts, programs, or commands that are executed within a project directory, making relative paths convenient for accessing project files. Absolute path always specifies the full path from the root. It is less portable if the file location changes or if the script is moved to a different environment where the root path is different. It is ideal for fixed locations or system-wide resources. Relative path specifies the path relative to the current working directory or another reference point. It is more portable within a specific project or directory structure, as long as the relative locations remain the same. It is ideal for files within a project or when the directory structure is known and consistent. At this example, we are going to demonstrate how to copy the contents of a file to another. This can be useful in various scenarios such as backing up files, duplicating configurations, or migrating data. We start by defining the paths for the source file and the destination file. The source path is where the file to be copied is located, and the destination path is where we want to save the copied file. The copy file function is designed to handle the copying process. It takes two parameters: src, the path of the source file, and dest, the path of the destination file. Once the source file is successfully opened, we read its entire content. Then close the source file to free up system resources. We open the destination file in write mode. If the file cannot be opened, an error message is printed and the function exits. We write the content read from the source file into the destination file. After writing, we close the destination file to ensure that all data is saved properly and resources are released. Finally, we call the copyFile function with the defined source and destination paths to execute the file copying process. This script effectively copies content from one file to another by reading from the source file and writing to the destination file. It handles file operations carefully, checking for errors at each step to ensure robustness. Now we will demonstrate how to manage log files by writing messages with timestamps. Logging is a crucial aspect of monitoring and debugging applications. By appending log messages to a file with timestamps, we can keep track of events, errors, and other significant occurrences over time. We start by defining the path for the log file. The log file path specifies where the log messages will be stored. The getTimestamp function returns the current date and time as a formatted string. This timestamp will be used to prepend log messages, providing context about when each message was logged. The write_log function is designed to handle the logging process. It takes one parameter, message, the log message to be written to the file. We open the log file in append mode. If the file cannot be opened, an error message is printed and the function exits. The append mode ensures that new log messages are added to the end of the file without overwriting existing content. We write the log message to the file, prefixed with the current timestamp. After writing, we close the log file to ensure that all data is saved properly and resources are released. Finally, we call the writeLog function with sample log messages to demonstrate how logging works. Each call to writeLog appends a new message to the log file with the current timestamp. This script effectively manages log files by appending messages with timestamps. It provides a simple yet powerful way to keep track of events and monitor the behavior of applications over time. The script ensures that log messages are written safely, handling file operations and errors appropriately. To rename a file in Lua, you use the os.rename function. This function takes two arguments: the current name of the file and the new name you want to give it. Old name is a variable that stores the current name of the file you want to rename. New name is a variable that stores the new name you want to give to the file. The os.rename function is called with old name and new name as arguments. This function attempts to rename the file. Success will be true if the file is renamed successfully, otherwise it will be nil. Error will contain an error message if the renaming fails. The if statement checks the value of success. If success is true, the message "File renamed successfully" is printed. If success is nil, the else block is executed, and the error message stored in error is printed with error renaming file. This code provides a straightforward way to rename a file in Lua, with error handling to inform you if something goes wrong during the process. To remove a file, use os.remove. This function takes the name of the file you want to delete. File name is a variable that stores the name of the file you want to delete. The os.remove function is called with filename as its argument. This function attempts to delete the specified file. Success will be true if the file is deleted successfully, otherwise it will be nil. Error will contain an error message if the file removal fails. The if statement checks the value of success. If success is true, the message "File removed successfully" is printed. If success is nil, the else block is executed, and the error message stored in error is printed with error removing file. This code provides a simple way to remove a file in Lua, with error handling to inform you if there is an issue during the removal process. File permissions can be changed using the os.execute function with the chmod command. The os.execute function is used to run an external command from within Lua. chmod 755 is the command being executed. chmod is a Unix command used to change the file permissions. 755 sets the permissions to rwxr_xrx, meaning the owner can read, write, and execute the file, while the group and others can only read and execute it. My file is the name of the file whose permissions are being changed. os.execute returns a status code. If the command is successful, success will be true. Otherwise, it will be nil. The if statement checks the value of success. If success is true, the message "permissions changed" is printed. If success is nil, the else block is executed, and the message "failed to change" is printed. This code allows you to change the permissions of a file using an external Unix command, with feedback provided on whether the operation was successful or not. This snippet changes the file permissions of my file to 644, reversing the previous permission change to 755. The os.execute function is used to run an external command from within Lua. chmod 644 is the command being executed. 644 sets the permissions to rw, r, meaning the owner can read and write the file, while the group and others can only read it. My file is the name of the file whose permissions are being changed. os.execute returns two values, success and error. Success is true if the command was executed successfully, and error contains an error message if there was a problem. The if statement checks the value of success. If success is true, the message, permissions changed to 644, is printed. If success is nil, the else block is executed, and the message, error changing permissions along with the error message error is printed. By understanding how to rename, remove, and adjust permissions, you can effectively control and automate file processes in Lua. This script demonstrates how to open a file in binary write mode, write binary data to it, and handle potential errors. IOOpen function opens a file named binary file in write binary mode. The WB mode indicates that the file is open for writing binary data. If the file does not exist, it will be created. If it does exist, its contents will be overwritten. String.char function creates a string containing the binary representation of the provided numbers. These are hexadecimal values, where 0xFF represents 255, 0x00 represents 0, 0xAA represents 170, and 0xBB represents 187 in decimal. File write writes the binary data string to the file. Since the file is opened in binary mode, the data is written exactly as is, without any modification. Then closes the file, ensuring that all data is properly written and resources are released. It prints a success message if the file was written, or an error message if the file could not be opened. The process is essential for handling binary data in Lua, where precise control over the byte content is required, such as when working with non-text files. Let us see how to open a file in binary read mode, read the binary data, and display it in a readable format. IOOpen function opens the file binary in read binary mode. The RB mode indicates that the file is open for reading binary data. If the file doesn't exist or cannot be opened for some reason, file will be nil. File read reads the entire content of the file into the content variable. The *all argument tells Lua to read everything from the current position to the end of the file. File close closes the file, ensuring that resources are released. The for loop iterates over each byte in the content string. String.byte function gets the numeric byte value of the I character in the content. String.format formats the byte value as a 2-digit hexadecimal number prefixed with 0x and prints it. %02x ensures that a single byte value is always displayed as 2 hexadecimal digits. %x formats the number as a hexadecimal value. 02 ensures the number is at least 2 digits wide, padding with leading zeros if necessary. For example, the byte value 4 will be formatted as 0x04 instead of 0x4, ensuring consistent 2-digit representation. This script ensures that it handles possible errors gracefully, providing clear error messages if the file cannot be opened or read, and properly formats and prints the contents of the binary file as hexadecimal values if everything proceeds correctly. Create directory defines a local function that takes one argument, which is the name of the directory to be created. OS execute attempts to execute the system command mkdir to create a directory with a name specified by dir name. The result is stored in the variable success. This will be true if the command was executed successfully, or false if it failed. The if success then block checks whether the directory creation command was successful. If success is true, it prints a success message. If success is false or nil, it prints an error message. Note that the behavior of OS execute mkdir depends on the underlying operating system. Remove directory defines a local function that takes one argument, which is the name of the directory to be removed. os execute attempts to execute the system command rmdir to remove a directory with the specified name. The result of os execute is stored in the variable success. This will be true if the command was executed successfully, or false if it failed. The if success then block checks whether the directory removal command was successful. If success is true, it prints a success message. If success is false or nil, it prints an error message. Note that the rmdir command will generally fail if the directory is not empty. In such cases, you might need a more comprehensive solution to remove the directory and its contents. The behavior of os execute depends on the underlying operating system. Ensure proper handling of directory names with spaces or special characters. rmdir typically only removes empty directories. Use caution with recursive removal commands. With these foundational skills, you are well equipped to handle various file and directory management tasks in your Lua projects.